Good morning, everybody. I'll just wait a couple more minutes for people to join, and then we will start. Okay, let us go ahead and get started. Welcome, everybody. So this is day number 6 of May Institute on Computation and Statistics for Mass Spectrometry and Proteomics. Thank you very much for joining us on this wonderful Saturday morning. We really appreciate that you are willing to spend time learning R, and we hope that this will be very much worth your time and effort. So let me just review again the logistics, right? So please use the Q&A box for all the questions and the chat box only if you have things such as, hi, how are you? And so on. And just maybe address a few questions that we have received since yesterday. So the Q&A of yesterday's session and also of today's session will be uploaded on the docs link today. So please come back for that if you would like. The videos of yesterday and today will be available. So yesterday, accidentally, they were made private. So we're working now on changing the permissions. So you will be able to have access to the videos very, very soon. So I see that one of our group members is working on it right now. And so otherwise, let me welcome back Ryan, who again is leading the discussion today. And I hope that today we will do more work on actually interacting with data and doing things which are really useful for the projects that you may have to do in your lab. And let me also welcome back our teaching assistants, Vartika Tiwari and Rohan Kapri. And Sai Laxmiato is also joining us today as a teaching assistant. So Vartika, Sai, and Rohan are PhD students in Curie College of Computer Sciences at Northeastern. Thank you very much for working with the questions and answers. It makes the webinar much more interactive. And for the participants, please do not hesitate to ask questions. We hope that we will be able to answer as many questions as you have before our time today ends. Thanks so much. And so, Ryan, please go ahead.
Great. Thank you very much, Olga. A special thank you for our TAs to really help and field these questions. Again, it would be great, please ask questions. That's what we're here to do, particularly as new R users. I think it's really important to be able to ask questions. No question is silly or not worth asking if it doesn't make sense. A lot of this stuff is, just learning about programming conventions, like rules that people just sort of set up about why we do things. And so if we can help answer those questions, I think that would be really great. And then thank you all to the participants here today coming in on a Saturday morning, afternoon, depending upon what time zone you're in. We did cover a lot of material yesterday, so thank you for sticking through that. I think really my main goal yesterday was to introduce some of the main pieces about the R programming language, and they may seem maybe a little disjoint, but actually there was sort of a theme of building upon sort of foundational building blocks. And hopefully if you start using some of these tools in your own work, you'll start to see how some of these ideas and concepts are really quite general about working with data, and that you can piece these tools that we introduced yesterday together to start doing some interesting things with data that you might work with in your daily work. Before we get into the content today, you may recall that we had some homework yesterday. You may or may not have time to do that. But what I'd like to do first is to go through those exercises that I had put forth that practiced the things that we talked about yesterday.
And Ryan, there's a
yes.
Question already asking if you could please review the data frame function before you start.
That would be great. Yeah, definitely. We're going to go through some examples here about this, and then please go ahead and re-ask questions if we don't cover what you're going to if we don't cover what you would like, and then I can answer those as well. But we will be working with data frames and functions on those as well. Okay, so step one, you probably know about the GitHub repository that we have for this project, for the session. If not, the TAs can post that link to you. Just to remind you about how you can get everything here in the repository. If you go to the main link here and you click on the code, you can download the repository as a zip file, and you will get all of the data here, all of the files, including the lecture slides. Just to note, we're going to be going through Intro to R Day 2 PDF here as the material for today. We also have some data here that we're going to be working with the exercises. This is a zip file that you'll have to unzip on your computer. And then we also have these exercises here that I'm going to be covering here in just a minute. We have here 2 exercises for day 1 that I'm going to go over. And we also have some exercises for day 2 that we'll cover at the end. One thing to note is that I've posted solutions for both of these. These are now in the GitHub repository. They weren't there yesterday, but if you were to re-download the repository files, you will find these solutions here. So that, and we're going to go over those live right now, but if you want to review these in the future, they are here for you to take a look at. All right, so what we're going to do is we're going to go through these 2 exercise files that I've put here, and let's use some of the best practices that we learned yesterday. Let's open up RStudio and make an RStudio project like we learned. So let me quickly redo that for these exercises. So as you recall, you can open up RStudio. We're going to go to File, New Project. We're going to make a new directory. We're going to make a new project. And then we talked about the 2 main pieces here. We need to specify where the directory is going to go for our project, and then the name of the directory. We noted that there were some other options here about creating a Git repository and some of these things over here. We can just leave those unchecked for now. We don't need to worry about those for making the RStudio projects. So let's do this example exercises is what I'll call my project. And this is going to go on the desktop just to make it easy. So we'll do this, and RStudio does its business here of setting up the project. Recall that this just creates a directory on our computer file system. There's really nothing too special about that. It's like any other directory. And if we want to get files like data or R scripts into this directory, we can just use our file browser to do that. So I had previously from our GitHub repository downloaded this as a zip file and unzipped it, and we get a new directory here for all the course content. And what I want to do now is copy, well, I have to unzip this exercise data file. And what I want to do is take these exercise files here, and this is in our file browser. So recall, this has nothing to do with RStudio. We're just using the file browser on our computer to take these data files and copy them into our new RStudio project folder that we just made. Okay, and if I open up that directory, as you recall, we can see those files there. If we were to go back to RStudio as well, we can look in the file browser and see those input files have just shown up here in our RStudio project directory. This means that we can now access them through scripts. Let's also get the examples that we have of the exercises. If we again come back to our repository that we downloaded on our computer, we can grab our exercises, and now the solutions also exist in here as well. So you can refer to those. So I'm going to drag these into our project directory. And then those also now exist in our RStudio project. Okay, so hopefully that was a lot of review yesterday of making projects and getting data into our project folders. Let's now take a look at the exercises that we had assigned for the homework yesterday. Okay, and this is going to practice the materials that we went through yesterday. So here's, let's see, let me show you actually what the exercises file looked like. I had given you a template here with some questions, and the idea was for you to go and you could write the R code here to answer these questions. Okay, and so what I've done is effectively done that in these solutions that we're going to review now. Okay, so here's the motivation. Imagine you're running an LCMS experiment and you have a 60-minute LC gradient that you're running. And so the first question was to create a variable called gradient min to hold the length of the gradient in minutes. So this is practicing two things. One, about creating a variable and using the assignment operator. So in this case, I gave you the name. You can recall that you can pretty much use any name that you want for your variables. There are some rules that we covered in the slides, and so those are summarized there. For example, you can't start a variable name with a number. There are some other kind of weird rules as well, but by and large, you're free to call a variable name whatever you want, and it's a good idea to use descriptive names that describe the kind of data that you're holding. Okay, so hopefully straightforward here. We name this variable gradient underscore minutes, and then we use this assignment operator that we learned about. Again, it was 2 characters, the less than sign and the minus sign. These things need to be smashed together. You cannot put a space between them. That's really important. And then the thing on the right side is the value that we want to assign to that variable. And again, if you want sort of a visual metaphor, you can imagine that the number 60 is being stored through this arrow into this variable called gradient minutes. You may also recall that we are working up here in the editor. And if we want to execute lines of code in the editor, there's a couple ways. We can put our cursor on that line and press run, or we can push Command or Control Enter, and it will execute this statement inside of the browser. Okay, and we can see that show up down here and it executed the statement. We were also looking at the environment, and so we can see that our environment now knows about gradient underscore minutes, and it's assigned a value of 60. We also know that we can come down here in the console and type the name of the variable as well, and hit return and also see its value. Okay, so hopefully that was fairly straightforward to do. The next question now is asking us to do some math expressions on the data. So this question here tells us to take this variable that we created with a gradient in minutes and convert it to seconds, and store it as a new variable. So again, we're going to use the same syntax here. Gradient seconds is the new variable name that I have. Use the assignment operator, and now we can do math on this number by simply referring to the variable here. We know that this contains a value of 60 minutes, and we're going to convert it to seconds by multiplying it by 60. We can execute that expression, and now we can see that our gradient seconds variable exists. R knows about it here. We've assigned it, and it has a value of 3,600, as we would expect. Okay, so hopefully pretty simple there, pretty straightforward about doing that with working with variables. We're building on that now with this idea of vectors. We learned about vectors as an object known as a data structure. You can think of this as a bag that stores data. And we learned how to do that using a function that goes by the name of C. It's kind of a funny, very short function name, but it stands for combine. And it says, I want you to combine these numbers into a single object known as a vector. And we can do that using this syntax here that we learned about yesterday. We already know how to assign variables, so there's no reason we can't take this vector and assign it to a variable. And so the idea here is that we've run some additional experiments with additional gradient times of 15 minutes and 30 minutes. And we want to store all of these together in a single entity known as a vector. And we're going to assign that to the variable called gradient minutes. Okay, so we're building upon our idea of variable assignment. Now this thing is a little more complex. It's a vector, but all the syntax is exactly the same. We can execute that. And now we can see over here in the environment that we have a new vector with these 3 values in it. Similar question is above, how can we convert all of these gradients, these 3 gradients now in minutes to seconds? And what's really cool that we learned is with vectors, we can still do math on them, just like we did with single values. So in this case, we can take our new variable called gradients with an S, minutes, and just multiply it by 60. And what's really cool is that we've now done essentially 3 math operations. We've taken this value of 60 and multiplied it by 15. We've multiplied it by 30, and we've multiplied it by 60. So we've done 3 mathematical operations in one short line of code. And if we can compare that back to what we did on a single number, the code is exactly the same, which is really cool. So doing essentially the code that we need to write to essentially do math on one number is effectively the same as doing it on an arbitrary number of numbers. Okay, so it makes it really easy to work with data. It's a really cool component of R that is used quite a bit to work with data analysis. So we can look at this gradient seconds variable again, either through our environment browser up here or through the console by typing the name and hitting return. Okay, so now we're going to get into perhaps a little more advanced, hopefully not too advanced, but advanced examples here. I gave you this vector here. These represent a bunch of precursor M over Z values for a given experiment. So I gave that to you, and you can just execute this code to get this variable in your workspace. We worked with pretty simple examples yesterday where you could easily tell how many numbers were present in the vectors that we worked with. In this case, you could still count them yourself, but we have code, we have computers that can help us do that. So if we use this length function, we learned about using functions yesterday, where they each have names, and then you put inputs inside of these parentheses, we can find out how long the length of this vector is. So let's do that. So if we type our nvals variable that we just assigned using the length function, we can see that we have 10 values here. Okay. And again, this is really useful when you have really large pieces of data. You want to count how many things you have. This is an easy way to do that. We learned other functions like min and max here. So there, we can use these same exact these same sort of function syntax on the vector to get the min and max values. And we can see these show up in our environment here. So we have a minimum M over Z of 338 and a max of 1041. So those are nice ways in which we can investigate the data that we have. We also learned other functions like mean, standard deviation, median, and there's lots of other math functions as well. And just as a reminder, if you want to learn about what a function does, you can type the question mark symbol and then the name of the function and press return. And RStudio will pop up a help browser here where you can go through, read about the function. Again, as a new user, you might find lots of this text to be a little bit, maybe a little bit difficult to understand and exactly what they're talking about. I would say as you get more experience with working with functions and working with R and learning some of the ways in which people talk about R, these instructions and help will make more sense. But at the very least, you can get an overview of what a particular function does and how it operates. Okay, and particularly in the details, there's usually detailed information about what that function is and what it does. Okay, so we did some math on a vector here, and we interrogated some properties about it. Now we're going to talk about using vectors and conditional expressions to start investigating the data in more detail. So what I'm asking you to do here is write a conditional expression to find values, M over Z values here that are less than 600. Okay, so using this vector, how would we write an expression that asks which values are less than 600? We learned about conditional expressions and that we could use operators like less than equal to, for example, to ask the question. Remember, conditional expressions allow us to ask yes, no questions about data. And so let's execute this expression. Let's take a look at the output and see what we get. Okay, so what we did is in this vector of M over Z values, we asked the question, which values are less than 600? And the computer responded to us with true or false values, essentially yes or no values, about whether or not that's the case. So we know the first entry is 968, and we know that's not less than 600. And so the computer responded false for that. And so we have 10 values here, one for each of the 10 m over z values in our vector, where this question was asked, whether or not that value was less than 600. Okay, so this was a conditional expression that we wrote. And what we can do now is use the idea of subsetting data. We learned about these square brackets that we can use on vectors to subset data, where we can take this vector of all of the values, use these square brackets along with a conditional expression here to get the values that are less than 600. So let's take that expression and execute that. And now we can see that instead of getting all of the values that are present in this vector, some are above 600, some aren't, using the conditional expression and the subsetting bracket operator, we're able to get just the values that are less than 600. Next, we had, again, hypothetical data here, but we're pretending that we have some charge states associated with the features that correspond to these precursor masses above. Let's make a new vector with those values. Then let's say we want to find the features here, the m over z values eventually for these features that have a charge state of 2. Again, we need to write a conditional expression. And a little bit of the tricky thing that we found about yesterday is that if we want to ask if values are equal to something, we have to use the double equal sign, two equal signs. And that was important because we also learned that we can use a single equal sign as another way to assign variables. Okay, I encouraged you all to use the arrow notation to do that, but the equal sign is another way that you could do that. So let me show you that. If you were to make this expression and put a single equal sign here, these two lines of code would do exactly the same thing. They would assign this vector to this variable name. If we want to ask the question, though, about whether something is equal to a particular value, we have to use the double equal sign. So that's just something to note. You'll probably make that mistake in your own code. I know I make that mistake every so often myself. It's just one of those things to note. So what this expression does is says for all of these precursor charge state values, which ones equal to 2? If we execute that, again, we get true false values where this question was either true or false. And then we can combine this conditional expression with our other vector above with the m over z values to get the m over z values for features that had a charge state of 2. Okay, and that's what this expression does here. All right, so that sort of worked with the vectors that we learned about yesterday and some various operations and ways in which we can subset that data in order to start doing some exploratory type analysis on our work. Any questions about that work, about those examples? And I would say, if any of those things were, didn't quite make as much sense, you can go back to the lecture slides yesterday. And in particular, if you look at, let me bring up the slides from yesterday. There are some sections here where, in particular, that we have these tables in blue. Let me find an example. So we that look like this. We have a few of these where we have some example codes and expected output. And so what I'd recommend is just practice these kinds of things. You can execute these lines of code in your own RStudio environment and look at your outputs, compare that to the expected outputs here, and also make some changes here and try some different ways in which you work with these things. And I think these concepts will make more sense as you start using them in practice. Great. Any questions, TAs, on going through these examples? If not, I'm going to go to the second example here. This is working with data frames. Let me move this over here. Okay, so we learned about working with vectors. We learned about variable expressions. We learned about using functions on vectors to get information about the data. Now we're going to transition to a slightly more complex case where we're working with data frames. And so we have some example data to work with. So first of all, we need to load this, this tidyverse library. that has some functions that we're going to use, in particular this function to read in CSV files. So we're just going to execute this. I had noted yesterday that you do see some output here. You don't have to worry about this output for all intents and purposes. It's nothing to be concerned about. I know there's this word conflicts here. I can cover that at the end if you'd like to know, but for the most part, this really shouldn't matter for the work that you're doing. So once we will have this tidyverse data, I'm asking you to go and look at this particular example data set that we have for the workshop here. This is actually some real mass spec data here. So it looks like some output from Skyline. And it's a CSV file, so we can use this function we learned about called read_CSV. We know that if this CSV file exists in our RStudio project directory, that we can just give the name of the file. We also found out, let me recall here, that if we call this function read CSV and we type the first few letters of the file name, if you press the tab button, it can autocomplete for you. And if there are multiple files that match that name, you can use the arrow keys and hit return in order to complete that full file name. So that's a really useful piece. There is a little additional optional argument here that I've included. When files are very big, R tries to guess what kind of data are in the files based upon the first couple lines in the file. And sometimes if you have different types that occur later down in later lines of the file, it may guess incorrectly. And usually it will warn you if that's the case. So in this case here, I put guess max equal to 10,000, telling it to assess the data on the first 10,000 lines to understand what's there. You sometimes, often don't have to worry about it. Sometimes you do. Let me give you an example of what happens if you don't put that guess max. So let me call this here. Okay, so let me run this function without the guess max if you were just to read it. This is a big file. It's about 200 megabytes here, so it's not necessarily a small file. You can see it's working here. And it gave a warning message to us. One or more issues, see problems for detail. So if you see this warning message pop up about parsing issues, you can use this guess max function. It may depend. There can be some complex cases where different things might be happening. But in this case, if we use the guess max and add more, let it guess on more of the rows, it will read the data file without a warning. So let's take a look at that. And you can see it did print some messages out about reading the data, but there were no warnings that popped up with that. Okay, so this is a table now. This is a rectangular table. So let's ask some basic properties about it. We're going to use some functions. One is nrow that we learned about. That gives us the number of rows. So this is a big table. This has, 1.25 million rows of data. We can use the ncall function to get the number of columns. It has 16 columns of data. We also learned about this dimension function, dim. And if we execute that function, it gives us both the number of rows and columns. It gives that back to us as a vector of values. And we also learned we could use our index subsetting using the brackets. If we wanted to get the first value, which is the number of rows, we can just type that variable. We can type, actually, we'd use the names. We'd use the output of that, dims dat, which is a vector. We could assign that to a variable, so dat dim. And then we can index that vector using the brackets and use the 1 to get the first element of that to get the number of rows, or 2 to get the number of columns. So oftentimes there are multiple ways to do things in R, and this is an example of that. If we wanted to get the names of the columns, we can use the names function. So let's execute that. This returns it to the names to us again as a vector here. And so we can kind of see what data is there. We also learned that if we just type the name of the variable and hit return, that we get this really nice output of the table. We learned that in the tidyverse ecosystem that we're working with, that these data frames are known also as tibbles in this case. So this is a tibble here, and we found that we could find lots of interesting information like the number of rows, the number of columns, and the names of the columns in the first 10 rows get printed out here. So this gives us an example of what the data looks like. I'm also asking you here to use the view function. This is really nice in RStudio. If you type view on that data frame, RStudio will make a new tab that pops up that gives us a table where we can interactively take a look at the table. It is sortable, so you can sort the data using these column sorters here. This is kind of a big data table, so it might take a little bit to sort, but it's a nice view of taking a look at the data that you can work with. All right, so this first question is asking us to retrieve the data from a column called file name in our data table. And we learned yesterday we could use this funny operator called the $sign that allows us to get any one of the columns in our data table based upon the name of the column. So if we type dat $file name and hit return, we get 1.25 million values here that correspond to all of the file names that are present in our table. So we got all the values from a particular column. Here is what happened. And if we call the length function on that, we can in fact see that there are 1.25 million values that came out when we did this. And that makes sense because if we ask about the number of rows in our data table, it is also 1.25 million. So that makes complete sense. We got all of the data in a given column across all the rows. And so those numbers should match as expected. We can ask how many unique file names we have by using the unique function. And again, we're combining that with this operator to get that particular column of data. We have 1.25 million entries of that, but in fact, there are only 12 of these values. So there's only 12 unique file names here present. Okay, so this is really useful. Use this all the time to, for example, count the number of unique proteins or peptides that you might find in your data. Now we're going to talk about a slightly more complex thing of subsetting the data frames. Let me recall, this was probably one of the most complex concepts that we learned about yesterday. In the slide deck from the first day here, we have this particular, let me go to the slide here. This was on slide 86 of the first day that talked about subsetting data frames. It worked similarly to how we subsetted vectors, but we had to give a row and a column selection here. So you can refer to slide 86 on the first deck that talked about that and some examples around there. But let me give you a concrete example here. I'm asking you to get the data for this particular protein. Well, actually, I'm sorry. Let me quickly look at the table so you can actually see what it looks like. View dat. That's always a good first thing to do, is take a look at the data table. This is a data table that has a bunch of peptide sequences assigned to proteins, along with values about them, like their charge states, their precursor mass, and the files in which they were found. So this question now is asking you, get the data for this individual protein here that we've highlighted here by this particular text. So you can do that using a variety of conditional expressions that ask about finding all of the rows where this protein exists. Okay, so that's what this conditional expression is here. And again, if we were to execute that in the console, we would get a bunch of true and false values corresponding to the rows where we find this protein. And we can just get all the columns here. So we put a column and then nothing else that goes after that. And if we execute that now, we now get a smaller table that only has 288 rows that correspond to all of the values for this particular protein. So we were able to subset our big table down into one for one single protein. Then we want to ask the question of how many unique peptides are present for this particular protein. So let's do that in two steps. Let's first get this subset of the data that we executed here and assign that to a variable here, just to make it easier. So if we execute this line of code, we have dat subset, which is a new table that has been filtered down that only has 288 rows that correspond to this particular protein. Then we can get all of the peptides for that protein by using the $ operator here to get the peptide sequences. That's what this expression does. So now if we print the peptides out, we have a bunch of peptides that correspond to this sequence, you can see there are lots of duplicates here because we have multiple measurements of these peptides. So let's get the unique peptides using the unique function. And so this variable is a much smaller set here. Looks like there's only 7 of those. And so now we can answer the question that for this particular protein, there are 7 unique peptides. Okay, so that might be something you might want to do in your experiment. You detected a bunch of proteins. You wanted to find how many peptides per protein that you have found, and you may want to plot that distribution to understand what that looks like in your data. And so we did this for one protein. We're going to see about how we could do this for a full data set in some of the materials that we did today. Just note that we did this step by step, and I think that's a nice thing to do to make things more readable and understandable. But you could chain these functions together with this nested structure where we call the unique function first, and then that output goes into the length function here to do essentially multiple operations in one line of code. I would suggest that you make things more explicit and use multiple lines of code just to make your code more readable and understandable. But as you get more experience, you may choose to make things more compact as well in one line of code. All right. So those 2 notebooks covered, all the large amount of material we covered yesterday. Again, just to remind you, in the Github repository, if you go to the exercises, these solutions exist here. So you can go through those in detail and play around with those afterwards as well to practice that material. Great, so let me pause here for just a second to see if there were any questions about that, about those particular solutions. And if you have any questions that you'd like to go into more detail, please write them down and we can cover them at the end of the workshop as well. Okay, great. So let's get into the material for today. And what we're going to be talking about to start is this idea of tidy data and how tidy data can be used in really interesting ways in combination with a set of packages known as the tidyverse to do some really interesting, useful, and powerful data manipulation operations, data analysis work in code that is relatively concise and readable. It's going to build upon some of the foundations that we had yesterday. We're going to learn a little bit new syntax, but I think you're really going to hopefully appreciate the power of tidy data and the tidyverse ecosystem for working with data. So we're going to have 2 main sections here. First, I'm going to talk about tidy data and what it is, why it's important, how to recognize it, how you can communicate to the people that you work with when you need to get data from them. You can ask them to help you get this data into the right format to make your job easier to work with data. And then after we talk about tidy data, we're going to talk about specifics working with a package known as dplyr that will allow us to build data analysis pipelines that are really flexible and powerful. And I think you'll find some really useful examples that you can take back to immediately use in the work that you do with data. So as I mentioned, we're going to start first about what tidy data is, why it's important, and then I'll give you a quick intro into what the tidyverse is and why it's something it's worth paying attention to with R. We're going to be using the terms messy and tidy quite a bit in this next sections. I just want to note that messy as a term, you might think of that as being bad, and that's not really my intent here. I don't really mean to give a negative connotation to messy. Essentially, what I mean by messy is that if data is messy, it's not in a form that's ready for data analysis. And so you may need to do some work to go from messy to tidy data, but it's not just necessarily bad data. Messy data could be bad, and you definitely want to work from that, but I don't want to imply just from the outset that if you find a data set somewhere that looks like it's messy, it's not necessarily bad data. Tidy, on the other hand, doesn't also necessarily mean that it's good per se. You could have tidy data that has fundamental problems or errors in it. So just because something's tidy doesn't mean that it's good. Tidy in this case just means that it's in some kind of format that's consistent and effectively ready for data analysis. In particular, in the R ecosystem, you'll see the word tidy data quite a bit. It's used quite a bit as a term. It has a specific meaning that we'll talk about. Other languages, maybe like Python or other pieces that deal with data, may use tidy in different contexts, but it has a very specific context in the R universe. Just to motivate things a little bit, one of the key people in the R ecosystem, his name is Hadley Wickham. He does a lot of amazing work with R. He was the person behind the ggplot2 package I mentioned yesterday for data visualization. He's behind the dplyr package that we're going to talk about today. He's a really big figure in the R community, and he likes to talk about tidy data in this regards. He uses this quote from Leo Tolstoy and then applies it to data. And the idea here is, he says that all happy families are alike, but every unhappy family is unhappy in its own way. And so when we apply this to data, essentially Hadley says that tidy data sets are all alike, but every messy data set is messy in its own way. And what's his point about this? What the point he's trying to make is that out in the real world, we encounter data that may not be well formatted, that may effectively be messy in a variety of ways. And one of the problems with that in terms of data analysis is that these messy data sets are like their own unique problems. They can have very distinct, very specific ways in which each individual data set is messy. It's messy in its own way. And the problem with that is we don't know how to reason about messy data sets. We don't know, necessarily where things are messy. We can't make any assumptions about the data. And as a result, every messy data set is like its own problem that you have to solve and work with. And we can contrast that to tidy data sets. Tidy data sets have a consistent format. And what's really useful is if we assume that we have data in a consistent format, we can reason about it. We can build tools around this tidy data format that allows us to build upon that infrastructure, allows us to build tools and ecosystems that allow us to take advantage of that common format. And that's effectively what the tidyverse does for us. And I think you'll see the power of that here as we go through the material today. So just as you probably know, out in the real world, usually data starts out messy in some way. Lots of reasons for why that might happen, but in any case, real world messy data usually means that it's hard to work with. It's hard to start doing analysis with it. It's hard to understand what's there. And so as a result, if we want to work with it, we need to usually get it into a structure to make it easier to work with. And that's what the concept of tidy data is all about, making it easier to work with, particularly with a programming language like R, where you need some consistent formats. Data can be messy in all kinds of ways. And so I have some examples here in the upper left. This is an example spreadsheet here of a teacher that's trying to track some grades here. And this is messy in the sense that there's a fundamental data table here that holds some, looks like some quiz and test scores here. But for example, this exists in the context of these other lines in this Excel spreadsheet. So this isn't an isolated table here. There are some rows here. There are some rows that don't have any data in them. You also note that these scores are mashed up together. It looks like they've written out a number with a division symbol and another number. So we have, looks like these are sort of number of points out of a total that have been represented in a way where the data is not isolated. It's not something that we can work with easily. So this is an example of a messy sheet that somebody might use to effectively visually keep track of scores, but isn't all that helpful for actually doing any kind of analysis or making summaries of the data. Sometimes tables are in PDFs, right? We really can't get access to these tables or maybe even images. Effectively, again, you can view the data using your human eyes, but it's not great for computers to consume and work with. We have proprietary MS data formats. This is a frustration if you actually want to go and read data in R. Somebody had asked, how do we read some raw MS files into R? And oftentimes that's not a straightforward answer and you may not be able to get to it. Sometimes you might just have badly formatted text files here. This is an example of a CSV file where the number of columns, the number of entries here that are separated by columns are not the same. So it looks like we have 5 values here and 3 values here. This is a badly formatted text file. Anyways, lots of examples where data can be messy, something to be aware of, and it causes problems if you want to work with it. in particular, sort of data that is unclear or unstructured makes it also difficult to understand what's there. If you look at a table and you can't even understand what's there, that's obviously a problem. Just some other points here about, why messy data is hard to work with. I'm sure you've probably encountered some examples in your own work where you've seen this. As I mentioned early on, that messy data isn't necessarily bad. Sometimes people present data because they want to present it maybe for visual consumption, which may not be perfect for working with computers. And that's okay. It doesn't mean the data is bad. So again, please don't necessarily think that messy data is bad data itself, but be on the lookout. If you have data that's really messy, that's not well organized, that could be signs of working problems with the data. Maybe somebody entered data wrong into a spreadsheet. Maybe there are other issues with the data. So I would say if you have messy data, be diligent, be on the lookout for issues that might be present. Now let's talk about tidy data in the context of the R ecosystem. Again, like I said, tidy data has a very specific meaning in R, particularly with the tidyverse ecosystem that we'll talk about. And it's really fairly simple and probably explanatory. The idea is that we have tables. Again, these are rectangular tables that have columns to them. Those are known as the variables. And these are the things that we are measuring. So if you're measuring maybe data about humans, you might want to keep track of their first name, their last name, their age, maybe where they live, or their zip code where they live. Those are all things that we're measuring. So those would represent the variables in our data. The rows are noted as the observations, and these are the things that we're making measurements on. So in our person example, each row would represent a person. And so each row would be a distinct person that we're making a measurement on. And then perhaps unsurprisingly, each value in our table goes into a cell. So a row and column in our table corresponds to a cell, and that's where we would record a value for that particular piece of data. Let me give you an example of a tidy data table here. We looked at this example data yesterday in our some of our examples here. And so one of the first questions you should ask about a data table is, what is this table about? Well, we don't have any additional context here, but we can probably guess here that these are raw mass spec files here. And each mass spec file refers to a particular condition, and then we have some replicate values here that describe sort of the replicate grouping of these particular files. Okay, so this makes sense. What does each row represent? So it's always good to ask the question, what does each row represent, and what does each column represent? In this case, each row effectively represents a mass spec run. The columns represent information about that mass spec run. For example, the file name, the condition, and the bioreplicate. So this is a nice tidy data table. Let me now talk a few notes about sort of tidy data in general, and then I think we're going to talk about some ways in which we might make that table even tidier. Tidy data is not the only way. So there are some data formats that may not fit in a nice rectangular structure, in which case you might need to work with other tools. But if you can get your data in a rectangular structure, then it's really nice to be able to make sure it's tidy, making sure it's in a nice organized table, like I talked about, with rows and columns that are well defined. Sometimes the relationships between the observations and the variables is not always clear. And sometimes you might want to swap those in certain contexts. And an example of that is in mass spec data in particular, like a protein group or a peptide table. Sometimes you have one row for each protein, and you might have lots of columns for the different experiments that you ran that measured that particular protein. Sometimes you might want to flip that around where each row corresponds to a mass spec experiment, and then you have multiple proteins per experiment. So sometimes the rows and columns need to be switched around. And so just be aware of that. And then sometimes tidy isn't always black and white. there might be different levels of tidiness that you need to get to depending upon your purposes. Some signs of messy data that you might need to tidy up. So let's take a look at an example. One case that you'll find a lot is data sometimes tries to mash up multiple pieces of information into a single cell. And this is not, strictly speaking, a tidy format. Every piece of information should go in its own cell. So in this case, we really should have separate columns that, in this case, take the gender and the age as individual columns, not in the same column there. So that's a case where you might have some problems with data that's not tidy. Some other notes here about variables and rows spread across multiple columns and vice versa. But effectively, you will get more experience as you work with data when things are messy. Let's take a look back at this table here about how we might make this table even more tidy. It looks like in this run column that we might have multiple pieces of information here that may or may not be useful to extract. So for example, it looks like here that we might have a date here, for example, of when this particular file was run. In certain circumstances, we might want to have that data. So one way to make this more tidy would be to extract this date out from this table into its own column called date. We might also want to pull out the sample number as well into its own column. So that's another case where you might want to make the table more tidy. Okay, but it all depends on your purposes and what you're trying to accomplish. All right, so that we talked a lot about tidy data. I was sort of hammering home the idea that it's really useful to get data into a nice, well-structured, organized, rectangular data table. So let's say that we have that data table. What can we do with that? In the R ecosystem, we have this idea of the tidyverse. And the tidyverse is described as an opinionated, I'll describe what opinionated means, collection of R packages that we can use for data science. Okay, and the idea is that once we know the general structure of our input data, mainly that it's a tidy data table, we can build all kinds of packages, all kinds of functions, all kinds of tools around the assumption to work with tidy data. And that's really a powerful thing to do. And we'll see that with a package known as dplyr here in just a minute. But here are some of the example packages here that are part of the tidyverse. We're going to talk about dplyr. I mentioned ggplot2 for visualization. We've used the readr package to read CSV files, but there's lots of other packages here in the tidyverse that's really powerful. I would suggest taking a look at the tidyverse website. You just Google for tidyverse and take a look at some of the packages and examples and help documentation that they have there that can show you about working with tidy data and why it's so important. I talked about some of these packages again, just highlighting some of the fundamental ones. ggplot2 is something to look into. dplyr, we're going to talk about. If you're going to be working with string data, I mean, we do that a lot when we're looking at peptide and protein sequences. There's this string R package that you can use to work with sort of data like that. Lots of other packages here. And again, the tidyverse website will go through some of these really, these great packages and examples about how you can use them. Okay, so this was sort of a lecture heavy section here of talking about tidy data and why it's important. Effectively, you want to think about your data in terms of rows and columns, making sure that each individual piece of data goes in its own cell. And if you can do that, then you've sort of gotten to a tidy data situation. Messy data is everywhere. And as you get more proficient with R, you'll be able to deal with it better. We're not going to cover all of the tools that you can use to sort of work with messy data. That could be a whole weekend workshop in itself because it's a really big topic. But again, if you go to the tidyverse website, there are packages that can help you deal with messy data and put it into a tidy format. And then the tidyverse ecosystem uses this concept to build upon tools to be able to work with data. We're going to be talking about one of those next. So let me pause there. Were there any questions about tidy data that you had? Let me briefly step out here and I will give you a live view of the tidyverse. So I'm just searching for that in Google. You take a look at the website here. It has lots of really great resources here, talking about the tidyverse, talking about what packages are present. I'm going to highlight this book here at the end, but if you go to packages, it talks about the core tidyverse packages. Each one has its own little section here. Let me just highlight one package. Here is the tidyr package. This talks about getting data into a tidy format. So covers some of the ideas that we had just talked about. There are some examples here. There's a cheat sheet that you can go to, and this links out to lots of different resources. So as you continue your learning about R and working with R, this is a great package to learn about, and you can dig into those resources here. Okay, great. We are going to take a break at 9:30, so in roughly about a half an hour. We didn't take a break yesterday. I apologize for that, but we will take a 15-minute break here, so I won't forget that. Oops. Okay, so let's give a next section. This is where we're actually going to start now doing some interesting things about data manipulation, building upon the material that we went through yesterday using a package known as dplyr. Okay, so the goal of this module is to understand the fundamental operations that underlie almost all of the data analysis work that a person typically does, and how these operations are implemented in this package known as dplyr. We're going to learn a little bit of new syntax today. It's going to look a little bit weird. It's known as the pipe operator. We'll talk about this, but this will form a fundamental structure for us to make data manipulation pipelines in this dplyr ecosystem that allows us to do data analysis work. So first of all, what is dplyr? So dplyr is an R package that's a part of the tidyverse ecosystem. When we load the package, we did that before using the library tidyverse command. When we loaded the tidyverse, we also loaded the dplyr package, so it gives us access to these functions. But effectively what it does is it defines these fundamental operations of data analysis that we're going to talk about. As I mentioned, the key thing is it assumes you already have tidy data. So if you have messy data, you'll need to get it into a tidy format before you start working with it. But once you do that, you can then start building these really cool pipelines using syntax that is relatively easy to write and read, but allow you to do complex analysis work in a way that's really straightforward and natural. And just as an example, in my day-to-day work, when I'm working with data, I'm using this dplyr package nonstop. This is a fundamental way in which I work with data, fundamental way in which lots of people that use R work with data. And before the dplyr package existed, we were using more of the base R way of working with data. When dplyr came along, it really changed the workflow. I mean, fundamentally changed the workflow on the way in which people work with data in R. So it's really an influential package for data analysis. So as I mentioned, this dplyr defines these data manipulation verbs. Okay, think of these as verbs. These are actions that we're going to perform on data tables. And these verbs are represented as functions. We learned about functions yesterday. So these verbs are just functions that we're going to use. The nice thing is that there aren't a lot of these verbs. So there's not 100 of these things. There's a small handful of these verbs, which makes it really easy to remember and work with. And really a key piece that, that you'll find with this dplyr package is it allows you to focus on the question that you want to answer rather than the mechanics of how you want to answer the question. Particularly, when I was a beginner working with programming languages, I could communicate it in words, the analyses that I wanted to do. I could tell somebody this is the kind of analysis I want to do, but oftentimes I would struggle using the code and syntax to be able to express myself in the language to get the thing done. The nice thing about these dplyr pipelines is if you can relatively straightforwardly and specifically state the thing that you're trying to accomplish, the code that you need to write oftentimes can flow fairly naturally from how you would say it through spoken words. So let's talk about these fundamental data manipulation operations, and we can relate this back to some of the material we covered in the first day. So first operation we're going to talk about is adding a column to a data table. So recall that all of this work that we're going to talk about assumes that you have a tidy rectangular data table. That is the fundamental assumption of what we're starting with. So one operation we might want to do is add a column to the table. And a use case for that is we have maybe data existing in our table, and we want to manipulate that in some way. For example, we want to convert the units of a column of data in our table, or we want to generate a new column that, for example, adds together multiple columns together in a new value. So this is an example of adding a column. Sometimes you want to pick specific columns in your data table. You don't care about some other variables. You want to get rid of maybe some useless information that you don't want to deal with in your analysis. So you want to pick specific columns. Alternatively, you might want to pick specific rows in your data. You want to focus on the data subset. You'll recall that we talked about some subsetting operations yesterday on vectors and data frames. These are those analogous operations here on the data tables. You may want to sort or reorder the rows in some way because you want to order things by maybe p-value, or you want to order things by retention time. This is an example of that. These last two are really important and powerful things that you end up doing a lot, where you want to take subsets of your data, group them together, and then compute summaries of those values. So let me give you an example. Maybe you have you want to compute differential expression on a given protein that's found in sick and healthy people. So one operation you might want to do is compute, for example, the average maybe intensity value or abundance value for this given protein separated out by the sick and healthy groups. This is an example where you would group by the disease condition and then compute a summary on that data in order to compute those. In the dplyr, remember I said that these operations are implemented as dplyr verbs, and these verbs are functions. So these are the verbs that dplyr uses. These are function names that we can use to interact with data. So mutate, we're going to add a column, kind of a strange name, but mutating, it's like we're adding a new sort of maybe like an arm or appendage onto our data table. So we're going to mutate it. Select is about selecting specific columns. Getting the rows is about filtering. So we talked about conditional expressions yesterday. We might want to filter certain rows based upon a conditional expression. That's what the filter data would do. If we want to reorder, that uses the arrange verb. So again, that makes sense. We want to arrange the rows in our table. And then we have group by and summarize, which directly follow from sort of the ways in which we describe those in English. We'll give concrete examples here in just a minute. So let's talk about how we use these dplyr verbs in our R code. So these are functions. So again, we need to give the name, and then we need to wrap the inputs around these parentheses. The first argument to a dplyr function is always the input data frame that we want to operate on. So this comes without exception. So all of these functions that I talk about, the first thing that you provide, the very first input here, needs to be the data table that we want to operate on. So in this case, if we use mutate with a data frame that we've assigned the variable my_df, this will add a column to my df. If we want to get specific columns, this select statement will select specific columns of my df. So again, this first input always has to be the input data frame that you want to manipulate. Some of these commands also have a bunch of additional inputs that you need to provide that describes how you're going to perform these functions. That's what these dots are. You're not going to type these dots in when you actually work in your code. This just means that there's going to be more inputs there for you to work with. Another important piece, just as the first input always has to be the data frame, the data table that you want to operate on, these functions give you back, they return a table that has been manipulated. So the input that you give is a table, the output you get is a table that's been manipulated in some way. And that's really important for how the tidyverse works.
Ryan, there's a question.
Yeah, please. Yeah.
Like asking, will we discuss merging tables and things like that in this tutorial today?
So let me cover that at the end. Table merges can be a tricky and challenging topic, but I will, let me make a note here about merges, and I can point you to some cases, again, in the tidyverse ecosystem where you can merge tables together. So yes, in fact, this dplyr package has functions to do that. We don't cover that there because it can be a little complex, but I will bring that up. So I made a note here that I'll cover that at the end. Thank you. Okay, so let's take a look here at how we might actually use these functions in practice. So this is the tidyverse package. We need to load that package up using the tidyverse. As I mentioned, that when we do this, this will also load the dplyr package that we're working with. We use our read CSV function to read in this annotation file here, and then we can assign that to a variable called dat. Okay, so this all covers stuff that we did yesterday. So hopefully that's straightforward. Now we're going to use this mutate command that will take this data frame, input data frame, and we're going to make a new column here in our data table. And what we need to do is write an R expression about what that looks like. You'll have to just get used to this a little bit, but this expression that we're going to write first is the name of the new column that we want to create. We use an equal sign in this case. It's a little strange, but we use an equal sign instead of the assignment operator. The reason for that is we're inside of a function here, and it's just a little bit of the quirks and the ways in which R works. But in this case, we use an equal sign, and then we write a mathematical expression that describes what the value of this new column we're going to create should look like. Okay, so let me come out to R and actually do this expression live so you can see what it looks like. Okay, so let's, again, we have our project here. It has this file present, so we've already loaded the tidyverse. There's no problem with reloading it. We can retype that command. If it's already loaded, it doesn't do anything. So, but there's no harm in doing that. Let's read our data table here, which is this annotations file. Again, we can type it to print it out to see what it looks like. It looks like this thing, same thing we saw yesterday. The goal now here is we're going to use this mutate command to add a new column onto the data frame. So let's take a look at this. Let me go through this again. Remember, always the input to these tidyverse functions needs to be the input data frame that we want to operate on. So that's why we're going to use the data table. And then we're going to make a new column. That column is called rep times 10. This is kind of a contrived example. We're going to multiply this bioreplicate column by 10. The data is not useful, but it's just an example here. So rep times 10. And then we're going to use the equal sign and then give the column that we want to operate on in the mathematical expression. Let's assign that back to the data table because we want to mutate it. Let's hit return. And now let's look at this table now. Okay, so it looks like the same table we had before, but now we have this new column here where we've done a mathematical expression on that. So we've manipulated the data table. We have a new data table out that we can work with. Okay, any questions on that? There is some new syntax here in how we actually define this, but hopefully it sort of makes sense with what we learned yesterday. Okay, let's go. So we're going to go through these verbs here to work with them. The select one. This is a fairly simple verb here. Select, again, get specific columns. Effectively, you use this to get rid of things that you don't want. Sometimes with mass spec data, I've seen some CSV file output files that might have hundreds and hundreds of columns in them when we only care about maybe 2 or 3 columns. So it's nice to just get rid of all that stuff. That's what the select function does here. And here's an example. Let's say going back to our example, say we only wanted to get the condition and bioreplicate columns. What we do is we use the select function. We use our data that we read as a CSV file. Then we provide a vector of the column names that we want to get. These have quotes around them, just to let you know. Again, R is a little bit weird about when you need to quote things and when you don't. you'll just get more experience as you work with R. But in this case, we have to put quotes around condition and bioreplicate as those columns, and it will give us back a data table that has those two conditions. So let's take a look at this. Let's execute that in our R environment. So we got rid of effectively this run and this rep times 10 column that we had added on here. And now we have just condition and bioreplicate. Okay, so that was a way to filter out, or sorry, select out, I should say, the columns of interest. Probably this next one is something I use every day. This has to do with filtering data. So we use this when we want to get specific rows, and almost always this is used in conjunction with a conditional expression. This is why we learned about conditional expressions yesterday, because they're used so often. They're used for filtering rows in your data table, and we're going to use what we learned about conditional expressions here to accomplish that. So in this case, you may or may not remember, but one of our examples yesterday was to get the rows in our data table where the condition column was equal to 4, condition 4. This is how we do it in this tidyverse example. We use the filter command. We're going to operate on our input data table, and then we're going to write a conditional expression. The exact same conditional expressions we wrote yesterday. There's no change to that. So we write those conditional expressions here, just as we did. Recall that if we're looking for exactly equal conditions, we have to use the double equal sign, and this will filter the table down to the rows where the condition is equal to 4, condition 4. Okay. I had talked about maybe filtering to peptides or proteins that had an FDR less than 0.1. This is exactly the kind of statement you would use to that, where you'd say the FDR is less than your threshold. We have the arrange verb here. All this does is just sort the table in different ways. So let's take a look here. And the key thing here is you have to tell the table how you want to sort it. So you probably do this in Excel. You probably use the sort function in Excel, and you have to give the columns that you want to sort on. You do the same thing here with the arrange function. So let's take a look at this in our studio. Okay. So in this case, we sorted the table based upon the condition column here. So it's just going to do an alphabetical sort in this case. Just as a side note and something of use, if we go back to our data here, there is this little helper function called DESC that stands for descending. So if you want to sort in the opposite order, you use this descending function around the column that you want to sort on, and that will reverse the sort. Let's see what that looks like. Okay, so these were in alphabetical order, no big deal. But if we put the DESC for the descending around that particular column, it's going to reverse the sort. So now we can see that condition 4 is up top and followed by condition 3. So that's useful. Sometimes you want to arrange your table based upon p-value, maybe based upon intensities and so on, and you can use the arrange verb to do that. Okay, whoops. Okay, this last example is where some real magic starts happening. I know these are kind of simple examples, but it turns out that you actually use these simple kinds of ideas and cases in more complex analyses. And this particular example is where things start to really get powerful. We talked about the two verbs about group by and summarize. These usually come together in pairs. You often use these two verbs in sequence. You first group by and then you summarize. And the idea here is that in your big data table, you want to group that table into smaller individual tables that you want to compute summaries on. So let's give an example where in our annotations data, we want to count up the number of runs per condition. We're going to do it as follows here. And this is a little complex, but let's take it step by step. The first thing we want to do is we want to take our input data and group it by one of the columns. In this case, it's going to be the condition column. Okay. We then, and to make it simple, we have to do this in 2 steps here. We're going to assign that to a variable called dat grouped. And then we're going to summarize on this group data frame to compute a new variable. the number of runs, which is just the length of the run column. This computation is now going to happen across the multiple groups that were part of the condition. Let me just give you the example live so you can understand what's going on here. So let's take a look at our data table again, just so we know. We want to count up the number of mass spec runs per condition. We have 4 conditions here. So essentially we want to do 4 operations. We want to ask how many runs for condition 1, how many runs for condition 2, and so on. So the first step that we want to do is we want to take this table and group it by the condition. Okay, so let's execute, and then we're going to save that to a variable called dat group. Let's run this. Just for information purposes, let's print out the dat grouped variable. Okay, so notice that it printed out the table that looks exactly like we had before, but there's some additional little information at the top. This is telling us that this table in R's memory, if you will, has now been grouped on condition, and that there are 4 of those groups, just as we expect, 4 of these condition variables. So this table, dat grouped, is not exactly the same as the original table, even though the output looks like it is. Internally, R now has this grouped as 4 separate entities, is effectively what's going on. Let's grab this summarize command here. And we'll walk through this. So again, we're trying to count up the number of runs per condition. So we're going to use the summarize verb. We're going to give it the grouped data frame that we have up here. And then we're going to compute a new summary here, kind of like we did with the mutate command. Remember where we made a new column here? We're going to compute a new column here, which is a summary. We're going to call that new summary n runs, and that is going to equal the length of the run. The length, the number of values in this run column for the group table. Let's take a look at that output. Okay, so this is really cool. We got a new table out here, 1 row for each condition, and then the number of runs that were associated with that. Again, somewhat of a trivial example here because we just have 3 runs per condition here. So all the values are 3, but we computed a statistical summary for each of the conditions in this, in 2 lines of code. Imagine now that you have a data table of proteins or peptides and you want to compute maybe the average mass error for a given peptide or protein. You might have, if you're to do that by hand, you'd have to do, thousands or, whatever of operations, the number of proteins or peptides you have in your table to do that. You could really effectively do that same kind of computation in what is effectively 2 lines of code. Okay, so really powerful. This group by summarize I use all the time. It is a fundamental part of working with data. Any questions about the group by summarize? Because that's a little bit more of a complex example. We're going to practice this with some examples as well. All right. Let's see here. It's almost 20 after the hour. Let's we'll take a break here in a minute. Let me get you set up with some practice time here, and then we can also merge that into our break here to give people a little bit of time here. So here's some practice time here. Essentially, what I'd like you to do is, and we did cover ththese live here, but I want you to load this annotations file up. I want you on your own to go and run the select and filter examples in the previous slide. I just want you to execute them. I want you to look at the outputs. I want you to sort of play with them in your own environment so you can see how you might work with these functions. Then I want you to think about how we did some of these things on day 1. Okay, in terms of subsetting vectors and data frames, and see how we sort of link these things that we learned yesterday to these new verbs here in the tidyverse. So you can take a look at some of the materials from day 1. And then I want you to try this group by and summarize example. And in particular, what determines how many rows and columns you get out after you do the summarize command? What's the key piece of information that informs that? So it's 20 after the hour. Let's take, you can use sort of 10 minutes here maybe to go through some of these examples. Let's come back at 9:45. We're supposed to have a 15-minute break. So you can maybe work through some of the examples. Maybe if you have some questions, feel free to ask them. But then we can take a break here for 15 minutes. And then we'll come back at 45 after the hour. That would be 12:45 Eastern, and then you can convert to your own time period. I will stick around here if people have specific questions on this particular material. And then when we come back, we're going to build upon all of these verbs that we learned about to start building some data manipulation pipelines that should be hopefully really useful for your work. Great. So we'll come back at 9:45. I will go through some of these questions here. So this is a good question about if you want to print all the peptides or proteins containing yeast, what expression should we use? Okay, that's a great question here. Let me give you an example here. If you want, yes, essentially, if you want to have more of a flexible way of looking for values in a given column, particularly with strings, there is a package here called string R in the tidyverse. So let's look at tidyverse. Sorry. Tidyverse is a package here called string R here, and this has some functions here that can allow us to search for patterns or detect patterns in certain strings. So let's take a look at, let me give you an example of how we might use this. Let me get my data loaded back up. Okay, so let's take a look at this data table. And let's see, I think it was in the protein name. I think was the question. Let me look at the Q&A. Yeah, so the protein name containing yeast here is the question. Okay. So we can use a function in the string R package. So we can load it called string detect, STRDETECT. We have to give a vector of strings that we want to work with. So in this case, we're going to use our data table and we're going to get the protein name column out. And then we need to give the pattern that then we're going to need to give the pattern of the thing we're looking for. So this is not going to do an exact match of the columns. It's going to give a match for a particular thing that we're looking for. Let's say we're looking for yeast. This is going to effectively ask the question about which protein names contain yeast in them. Okay, and some of those are true, and some of those are false. Oops. Okay, so let's take a look now at using our subset command here. So let's take our data table. Let me come back to our. This is effectively a conditional expression. It's asking the question using the string detect function where yeast occurs. We can take our data table and use our data table subsetting operations to get this. So let's call this dat yeast. Okay, so this is one way we can do it. And now if we take a look at our dat yeast table, let's see here, let me make sure this makes sense. Let's take a look at maybe the first couple of these. Okay, so you can see these are the first couple of ones that have yeast. I think all these proteins have yeast in them, to be honest with you. So this operation did not give us any subsets. But if you had multiple organisms here, for example, you could use this kind of way of working with the file to do that. Let me post this into the, I guess, the chat here. Example. Okay. So there's one way you could do it. Another way you could do this is with the tidyverse operations. Let's take a look. Let's use the filter command. So we could also have typed, let me grab that conditional expression, which is the string detect. We could also have used filter on that data table and given that conditional expression as well, just like that. And that would have done the same thing. And it's a big table, so it prints out a lot of things. Again, it didn't do anything interesting in this case because everything has yeast in it, but that's an example case. So you could use something like that in your own data if you wanted to get like the human proteins or the yeast proteins or whatever proteins you have. Okay, this is a great question. How can we filter out like contaminants or decoys, etc.? I think this is a great question. We have an example of this. Let's take a look in our GitHub repository. Okay, we're going to go over this. How would we filter out? Things like the decoys? We're going to go over that. So and it's in one of our examples here. But effectively, we're going to use our filter command like we used before that will enable us to effectively filter out, get rid of things like decoys and so on. So we're going to go into that. But if I don't answer your question, please, let's go over it again so we make sure it makes sense. Great. There was a question about sorting columns alphabetically. Great question. So we have a verb for that. So here's a little cheat sheet. So and it's great. It's great to be able to, that's the key thing with tidyverse is sort of being able to say what you want to do, what you're trying to accomplish. And if you can say it, then you can usually do it. So if we want to sort columns alphabetically, that is this arrange verb here. Okay, so we're going to use the arrange verb here as part of the tidyverse. And then if you take a look at the arrange examples here, this was an example where we did that. So we alphabetically essentially arranged, sorted the table based upon condition. If you had numerical values, it would sort based upon the numerical value. And then if you want to reverse the sorting, you can use this descending function on the name of the column you want to sort by, and that will reverse the sort. All right, if you're still here, I'm going to go and refill my coffee, but please keep asking the questions in the Q&A. I think that the TAs will field some questions, or I'll continue to field them in a few minutes when I get back. But yeah, please keep the questions coming. Thank you. All right, it's coming up on 45 minutes past the hour here. We'll get started in just a minute. So we'll give it just a few more seconds here to let people come back. There were some good questions that came through, so I will cover some of those live here. But before we get into that, let's just go over some of these examples here and take a look at some of these live. So the first thing we needed to load up our example data here. So we will execute these 2 lines of code. Again, it's this table, this simple table we've been working with. And I think what I asked you to do is to go and take a look at the filter, the select and filter examples from the previous slide. So let's take a look at those. Here's the select command, and the idea was here to get the condition, get only the condition and bioreplicate columns here. So we use the select command here. So again, we can use the select verb. This is a function here. We must give the input data frame that we want to work on, and then we need to supply a vector of column names that we want. So I think we said condition, and I spelled this wrong. So let's see what happens. Let me not fix that. Let me leave that error there, and we can see what happens if you happen to spell a column wrong. Okay, so it gave us an error. Well, I spelled them both. Oh yeah, no, sorry. I guess I got bioreplicate right. It spelled condition wrong. It tells us that the column condition without the I after the D there doesn't exist. So this is a case where you actually got a helpful error message. So let's go and fix that typo by putting the I there. And then if we run this piece of code, we in fact get the data table out with just the condition and bioreplicate. Let me cover this in parallel, but one of the things I wanted you to think about was, does this look familiar, getting specific columns from a data frame? And can you do this using alternatives from day one? Well, let's think about what we learned in day one. We learned about the subset operators for using the square brackets. And we also learned about if you want to subset tables, that we need to give a expression that represents the rows and expression that represents the columns that we want to get. And if we want to just get all the rows or all the columns, we just leave that particular piece blank. So in this case, we want all of the rows in the data. So we don't need to put anything for the row specification. We just leave it blank. And then we just need to give the vector of column names that we want. And so we do this here. And if we were to execute this line of code, we'll get the same output. So these 2 lines of code effectively do the same thing, 2 ways of doing the same thing. But you can see they're sort of very similar. The code isn't all that much different. We have very similar use of vectors here to how to get the data. Let me take the second example. This was using the filter example. Okay, let's go there. Filter. We wanted to get only the rows for condition 4. All right, so this was the code for that. I can just type it here. Filter dat. We have to write a conditional expression. That's what usually the filter command works with. And so we want the cases where condition equals condition 4. Let's execute that line of code. And we can see that, in fact, we only get the rows in the table where condition equals condition 4. And again, going back to the material we learned on day one, we can do a similar kind of thing here. Just really important to note, select is about getting specific columns, and that's why we had to give the column specification here, the second piece after the comma here to get specific columns. For filtering, this is about getting specific rows. So now we have to give the row filtering option here instead of the column. So in this case, we have to specify the same conditional expression here. And if we want all the columns there, we have to put a comma. That's really important. But we have to leave this last piece blank because we want all the columns. And if we execute that, sorry, this was a good error. I'm glad I made this mistake. It says object condition not found. In this case, we actually have to supply a vector of the conditions we want to filter in. And those columns exist inside of this data frame here. So we actually do have to put the dat and the $sign here to get these condition values here as a vector to make this logical expression here. If we execute that, we get the same table. Why didn't we have to put that $sign condition inside of the filter function? The reason is that the tidyverse, this is how the tidyverse work and how these functions work. Effectively, because the first argument is this input table, the function knows that it needs to look in that table to do things. So it helps us reduce code by, we can refer to columns specifically in these functions because it knows what data table we're working with. So it's a little bit of a shortcut. It allows you to write less code, but it is a difference between using the filter commands and the mechanism that we saw yesterday. Any questions about that? Let me continue with some of the questions that came up. So there was one about arranging, I think, by multiple columns. That's a great example. So let's take a look at the data table. I think we wrote some code here where we used the arrange function with our data table, and then we supplied the condition column that's saying that we want to sort this by condition. And if we ran that, it would arrange the table. It turns out the table is already sorted, so it didn't do much for us. But let's say you want to do additional columns, though. We can then put, we just put a comma and just keep adding columns there. So we could put bioreplicate, and we could put run there if we wanted to. And it will sort first by condition, then by bioreplicate, then by run. Exactly the way that Excel would do it if you were to do the sort function in Excel. Another thing we could do is, let's do, there's no reason why you can put the descending option on any one of these. So we could do descending on condition, for example, and then sort by bioreplicate in its natural order and then by run. So you can do these kinds of manipulations where you can do descending order on one column and not on another. So it's up to you, but effectively you just keep going with the number of columns if you want to keep adding additional columns that you want to sort by. Okay, there was a question about, this is a more complex example, but I like it. Let's read our bigger table here, the input table here. This is, again, the bigger table with all the proteomics data. This will be a fun one, I think, to work with. We work with this in some of the examples. It's more maybe like a real world example of data that you might have. Oops, I didn't put the guess max, so we got this warning message. This is what I talked about this morning. We'll just put 10,000 there. And this is a big table, so it takes a little bit to read, but it came back. So let's look at this. And probably I think what somebody noticed is that there were some decoys here that we may want to filter out from our table. Okay, that might be a common command, a common thing you want to do. So I think the first thing to note is what dplyr verb would you want to be able to accomplish that filtering? Well, it's the filter command. Then the next question is, how do we filter out essentially protein names that start with decoy? That's kind of the key thing. And we didn't explicitly learn how to do that, but let me point you in the direction of where you might want to go to do that. And what we can do is, if you go to the Tidyverse, let me go there, the Tidyverse main website, there is a package called string R. The string is what computer scientists like to refer to as data types that are represented by letters and words. Okay, those are known as strings. Just as some background, so this string R package allows us to do some things about strings. This is a little more advanced. We're sort of digging into documentation here, but there is a cheat sheet here that you can take a look at. And let me focus in on a function that might be of use to us. This function that is string starts, and it says detects the presence of a pattern match at the beginning of a string. Okay, so that sounds useful. Essentially, we can ask if a string starts with decoy, filter that out. So let's take a look at how we might write this expression. So let's use the filter command on our, this is the big data that we just read, dat. And then we need to give a conditional expression. We're going to use the str starts function. This gives us a little bit, again, this is a little more complex, so just bear with me here. We need to give the things, essentially the columns that we're interested in filtering. In this case, it's going to be protein name. Protein name. So it says, look in the protein name column, and does the string start with decoy? And you got to spell it just as you see it, D-O-C-O-Y, decoy, here. Let's take a look actually at this as a separate expression and just execute this. This is a conditional expression. It asks, and sorry, I'm going to put the dat here. You're going to see why we're going to need to do that and why we don't. This follows on what I just mentioned here, but it's going to ask for all of the protein names inside of the data table in this column. Do they start with decoy or not? And if we execute this, we're going to get a big, long vector of, in this case, 1.25 million answers that come out. Some are true, some are false. And this is going to answer true when the decoy, when this expression is true. We're going to add just a note to take. We want to negate this expression, so we can put the, do you remember yesterday we talked about not equals, and that looked like a exclamation point and an equal sign? The exclamation point does like a negation kind of thing. So we can actually just put an exclamation point here into the expression. So this says, gives us all the protein names that don't start with decoys, effectively what that says. Okay, so let's take a look at the output of this. Now you can see that some of the first rows in the original table here started with decoy. If we do this filter command here, we got rid of those rows that started with decoy, and now we get proteins that weren't detected as decoys. Okay, this actually specific cases inside one of the examples. Let me copy and paste this code, if I can, into the chat. There. Okay, so that's an example where we filtered out the decoys from the data table. Something very common you might want to do. Easy to do that. One last question that came up, a good question. They had seen this expression where there was a colon operator with two numbers on either side. In some programming languages, you use this colon operator to select rows and columns. That's not the case in R. This actually is another operator that does something else. The cool thing about programming languages is that you can experiment. And so if you have a question about like, what does this colon operator do? I would suggest just go and make an expression and write it and execute it and see what happens. So let's execute this. So this colon operator just made a list of numbers for us, the numbers 1 to 10 for us. It made a vector of numbers 1 to 10. So for example, if we took our data table and used this colon operator to go with the numbers 1 to 10, that will give us the first 10 rows of the table. Or we can even put 1 to 5 there, that gives us the first 5 rows. So that's a handy way to make a vector of numbers from one, from a start to an end. I should say a vector of integers, really. All right. Okay, great questions. Any follow-up on that? So what we just did is we got the foundations of these data manipulation verbs that are implemented by the tidyverse package. We're going to expand on this now in a really cool way to allow us to do some interesting data manipulation work. Let me just remind you again, these are the verbs that we talked about. These represent the fundamental data manipulation operations that we can use to do really cool analyses on data tables. Okay, so let's get into this last component of the workshop here. We're going to be talking about analysis pipelines. Yes, so like I said, we're going to talk about analysis pipelines. We need to learn just one other bit of new R syntax, and this is known as the pipe operator. And this is another one. R has all kinds of these weird operators. We know the assignment operator looks like an arrow. We've seen the $sign that can allow us to access a column from a data table. This is yet another one known as the pipe operator. And you can think of this operator as taking input from the left side of something and feeding it like a pipe over to the right. That's why we're using this little arrow, this greater than sign to look like an arrow. So something from the left is going over to something on the right. And we use this in regards to functions. I'll show you what I mean in just a minute here. This is 3 individual characters here. It's the %, the greater than sign, and the %. And these, like the assignment operator, you cannot put spaces between these. These all have to come together. It's a weird operator. It just kind of is what R is, and kind of consistent with R sometimes doing funny things with these symbols. And the general idea here with this pipe operator is that we can take a tidy data frame and we can pipe that data frame into one of the dplyr verbs that we just learned about to now produce a modified data frame. Okay, so this is a powerful concept. Taking a data table, piping it into one of these verbs and getting out a modified table. So here's the general template here. If we take a tidy data frame and we pipe this into the mutate verb, we're going to get a new data table that has a new column, because we know that the mutate command adds a new column. If we do the same thing with select, we know we're just going to get a table with the columns that we selected. If we do this with the filter command, we're going to do the same thing with filtered rows. All right, so that's the general template of how we're going to be using this pipe operator. So let's just do some quick practice with the pipes here so you understand what's going on. This is some code that we saw, several slides back about filtering a data table based upon the rows that had conditions that were equal to condition 4. This is code that uses the pipe operator. And what I'm going to tell you is that these 2 lines of code do exactly the same thing, just slightly different. So can you spot the differences where these 2 lines of code are similar and different? Probably not too hard to see that essentially what happened was we took the first input of the function and we moved it out in front of the expression. We added this pipe filter, this pipe command. Then we have this filter function call that looks exactly like the same thing that we had before, but it removed that first part. Effectively, we just take this first part and move it out in front, and then everything else is the same. Okay, so it's 2 ways to do exactly the same bit of code. And you'll see why this is going to be really powerful in just a second. So let me, maybe I'll run through these live here. Wanted you to practice with pipes a little bit. So let's look at this particular, let's go back to our annotation data. And I wanted you to rewrite this example using the pipe syntax. So probably, hopefully not too complex. Let's take a look. Let's read our annotation data again. Okay, so this was the code. This was the arrange syntax. We saw this before. I won't assign it, so we can just look at the output here on the table. So let's arrange this by condition. I tell you what, let's make this a little more interesting and arrange it in reverse alphabetical order. How would we write this with pipes? Like we saw, we just need to take the first argument out, stick it on the front, add this pipe operator, which is percent greater than percent, and then take the exact same stuff that we had before, but take off that first part. Okay, so let's run this code. And you can see the table looks exactly the same as that we had before. So this is exactly the same outputs that we get, just two ways of writing the same things. Okay, so hopefully that makes sense. Here's another little piece. Make a vector with the values 1 to 5. We can maybe learn some new syntax that we just reviewed just a few minutes ago and assign it to a new variable, and then write the code to get the maximum value of that vector. Okay, so let's do that. Let's myvec. We just learned this colon syntax. We know that this makes a new vector with the numbers 1 to 5. So that would be one way to do it. You can print this myvec out. And this is in fact the vector with the values 1 to 5. We could have also have done this, which we did yesterday. Right, same thing. myvec. Okay, and then I asked you, how would you get the maximum value out of this vector? We learned about the max function, so we can say myvec. And we can get the max value out, which is 5 as expected. That's good. Then I asked you, can you think of a way in which we might use the pipe to write the same expression? I don't think you should do this in practice. This is mostly just to practice with the pipe to understand what exactly it's doing. Remember, the pipe just takes the first argument and moves it out in front. So we could rewrite this in pipe command here by writing myvec and then piping that into the max function. If we execute that, we get 5 out. Okay, again, in this case here, this is actually harder to read in my mind a little bit. I think if we just typed max myvec, that maybe makes a little more sense. It's saying get the maximum of my vector. Okay, so in practice, I don't suggest you do this, but I wanted to bring this up just to hammer home the point that all this pipe is doing is taking the first argument of the function and moving it out in front. All it's doing. Okay, it's going to be really helpful though in these dplyr functions that we just learned. Any questions about the pipe operator? TAs, go ahead and interrupt if there's anything we'd like to.
Yeah, there's a question of what would be the advantage of using the pipes.
I love that. That factors into what we're going to be doing here in the next slide. So thank you for that great segue. Appreciate it. Okay. Oops. My goodness gracious. 1 second here as I get my computer together here. Okay. Here we go. So here's the key piece, I think, of today's material that we're going over. The pipe operator can chain together multiple verbs, which becomes a pipeline. So a couple things that we learned today. One, we learned about tidy data frames, rectangular data tables, which is great. They're well structured, well organized, and they're great for working with them in R. We learned about these dplyr verbs that manipulate data tables, functions like mutate, filter, select, and so on. We also learned an important piece that the first input to a dplyr verb is always a tidy data frame. We also learned that the output from a dplyr verb is always a modified data frame. Okay. And then we just learned with the pipe operator that the pipe operator takes that first argument out and moves it to the front. So hopefully maybe you're seeing a chain here of sort of logic about how we can combine these concepts together into a useful thing for data analysis. So here's the idea. A tidy data frame is our input, and we can pipe that into a verb. That produces a modified data frame. It just so happens that data frame is itself a tidy data frame. So there's no reason why we couldn't take that output and pipe that into a dplyr verb as well to produce another modified data frame, right? And so the magic that happens here is that we can start creating these pipelines where we start with a tidy data frame and pipe them into different verbs over and over again to do a complex data analysis task. Okay, so this is a really cool piece of the dplyr package. And again, before this dplyr package exists, essentially I did my data analysis with lots of the other tools we learned about on the first day. But when dplyr came out, it fundamentally changed how I approached and thought about data using this pipeline syntax. And it's really powerful. It's really readable. Let's see how that works. This is an example, again, using this small data table, this annotations table. So maybe not the most interesting, but it's a small table that we can use to work with to get some examples. And then we can work with the larger data table with some examples here to do maybe some more interesting things. Okay, so let's say your boss or somebody gave you this admittedly somewhat silly contrived task, but just hear me out here. For this annotations table, I want you to get the rows that have a bioreplicate value of 2 or higher, and then count up the number of runs per condition. And then the table I want you to give me on the back end is going to be the results, but I want you to sort them in descending order. Okay, again, a little bit of contrived example, but these steps here could be anything. Take the protein table, filter out the decoys, count up the number of peptides that you detected per protein. For example, that might be the task. And that's a fairly complex task to do. In Excel, that would be, I don't know, probably pretty challenging to do. I don't even know if I could do it, frankly. But in any case, this is where a pipeline works really well. So we load up our tidyverse package because we want those functions. We read in our file. Now we're going to write a dplyr pipeline that accomplishes this task in just a few lines of code. We take our input data table here, and we filter to the cases where the bioreplicate is greater than or equal to 2. We then pipe the output of that filtering command to a group by verb here, to group by condition, and then you summarize to count up the number of runs per condition. And then we take that output table and we range that in descending order based upon condition. Okay, so effectively, and look at this code, I think it's really cool that the code this is still our code, right? This is not English, but it does read about what we talked about above here. So take your data, filter it where the bioreplicate is greater than 2, and then I want you for each condition to count up the number of runs and then arrange the table by condition. Okay, so I sort of translated these words into English here, and that's the idea. If you can say these things sort of in English, oftentimes the code that you need to write in order to accomplish them is fairly straightforward. That's not to say that obviously you're going to need lots of experience with R and get more expertise and get more comfort about working with R in the language, but effectively it becomes more straightforward to write these kinds of pipelines. Let me talk a little bit about the syntax here and some conventions here. You can imagine if you string these commands together, they can get very long. You can get very, very long lines of code. And as a result, it's very common to separate each step on its own line. Okay, and that's okay to do as long as you put the pipe command at the end of every line. Okay, so the idea is you start with your data frame, you put the pipe command, then you go to a new line, and then you write one of the verbs followed by a pipe command. Go to a new line, go to the pipe command, and so on. Okay, so it's a little weird. It's not one line of code. R treats it effectively as one expression, one line of code, but we add these lines just to make it easier to work with and easier to read. So let's take a look at this pipeline here. Okay, so let's read this data table here. Let's take a look at this pipeline. Oh, yep, and even my PowerPoint slides sort of put it on multiple lines. So I'm going to make this easier to read here. And let me execute. Let's take a look at our table. I'm going to execute the entire pipeline here. And we can take a look at the output, and then we'll look at the pipeline step by step. Okay, so what do we expect? We expect the bioreplicates only to be 2 or greater. We want to count up the number of runs per condition, and then we want to arrange in descending conditions. So let's take a look at that output. Okay, so a couple things. It did what we wanted to. It got rid of condition 1 because of the filter command. Then it grouped by the conditions, the 3 remaining conditions, and counted up the number of runs there. There are 3 of them. And then it ordered the table in descending order of conditions. So we went from 4 to 3. So again, a little bit of a contrived example, but I think hopefully you can see that this is really quite general and can be powerful. One thing that can be useful is to take these pipelines step by step. And one way you might want to do that is you can just take your cursor and copy the piece of the pipeline before the subsequent pipe operator. We can copy and paste that into our console and execute, and we can see what it did in that first step. In this first step, it got rid of the condition 1 rows. Let's do the next step. We're going to now do the group by piece. If you recall, the output doesn't look any different, except that it tells us that we now have a data table. This is in R's memory that has been grouped by the condition column, and there are 3 of those things, which is correct. Those 3 of them. We can then go and do this summarize command to count up the number of runs per condition, because we're operating on a data table that has been grouped with the group by. So let's take this piece of the pipeline. We'll run that. We now have a new column called n runs, and that's equal to the number of runs on those conditions. And then this last piece is to sort this in descending order of condition. So we do that, and in fact, we get our final table out here. In practice, usually what happens is I will start with a pipeline, and I will usually work it step by step. So I'll say, okay, I want to filter this. Let's find bioreplicate equal to, I don't know, 3 in this case. And I'll usually go and I will execute this code. We learned yesterday that if we put our cursor on a line like this one and push command or control enter, it will execute that code in the console down below. Nice thing about these pipelines is, even though this is on multiple lines, our studio knows that this is really a single expression. So we can put our cursor on either line here, it doesn't matter, and hit command or control return, and it will execute the entire pipeline no matter how long it is. Okay. So typically in practice, when I work with these pipelines, I usually build these up step by step, and I look at the results on the output to make sure it is what I expect. And then, okay, if that looks okay, then I will continue with the pipeline and continue to write them. Right. We are going to take a look at some more interesting examples, but before we get to those, any questions about dplyr pipelines? So hopefully, I think you can see that these pieces here can really be used and maybe built up to do some interesting things. All right, let me now go to, let me remind you, in our GitHub repository, under the exercises, we have some day 2 dplyr basic exercises here. We're going to be doing some things with that larger data table. I will post the answers after the course, the solutions to these exercises, but let's walk through these live, and then please let's ask some, if you have questions about things, if things don't make sense, let's talk about those. Okay, so let me come here. So I'll walk through these questions with you. So the first thing we want to do is load up the tidyverse, because we're going to be working with tidy data. Oh, I noticed I have a little typo here. I'll fix this in the solutions before I post them. But in any case, this data file is inside of our directory, because we copied those earlier this morning. We're going to read this big data table. This is the one with all the peptides from a large proteomics experiment. And this may take a little bit to read on your computer. Again, let me just orient you to what this thing looks like. We have a bunch of peptides that have been detected. We have some attributes about those peptides. We can use the view command. Remember, if we type view with a capital V on the data table, that RStudio will pop up the data table. So we have a bunch of detected peptides. We have their charge, their M/Z values. Looks like some product ions as well. And then we have intensity values. These are in different files here. So we have multiple. There are replicated rows for the peptides because we're measuring these peptides in multiple, essentially mass spec runs. Okay, so this is probably a data table that, if you're doing mass spec proteomics, you probably have tables like similar to this in your own work. Okay. So first question here. Remember yesterday we filtered, or I think today, I guess, we filtered to this particular protein. And we did this using the subsetting syntax. Let's do this using the filter command. So we're going to use our pipe operators now because we're going to be doing some pipelines here. So we're going to take our input data that we just read. We're going to use this filter command where the protein equals this particular one. Okay, so let's execute that code. I assign that to a variable .subset. Subset. And that's this new table. Remember, the original table had, 1.25 million rows. This particular subset has 288 rows, okay? And should correspond to just this particular protein. I think it's useful to always check data as you're working with it to make sure things work as expected. So how might you confirm that this DAT subset really has data for just this protein? We can use information we learned yesterday. So one thing we can do is we know if we type the data frame and we type the $ and then the protein name, column name, and we hit return, we can get all of the values. Sorry, we want that subset, right? That subset, we can get all the protein names for this subset, and we can hit return. And it printed all those out. Visually, these look the same, but I would never trust your eyes. So let's use that unique function that we learned about. Unique dat subset with protein name. And in fact, all the unique values for this vector of protein names is in fact this particular protein that we got. So that's a way to check data. I highly recommend doing those kinds of checks with your data in your analysis as you're doing analysis, just to make sure things look as expected. Okay. How many rows and columns did you get when we did this filtering command? And how does this compare to the number of rows and columns you got when you subsetted? Okay, so this is just nailing down the point that the original data frame had 1.2 million rows. This subset has fewer number of rows. These are 288 rows here because we subsetted data. As we expected, we'd expect to get fewer rows. We could have also typed n row, right? We know about that function to get 288 rows. If we were to do syntax from yesterday, we could do the same kind of expression where we give a row filtering conditional expression. Okay, just the same way to do that. Okay, let's say we want to get data for a particular file name. So not only do we want for this row, for this protein, but we also want to look at the particular sample. Imagine you're running some data. One of your MS runs happens to be an outlier in some way. Maybe the tick looked strange for it or something, and you want to look at that specific data. Well, we can actually combine this filter command with the pipeline into another filter that first filters by the protein and then filters by a specific mass spec run. So that's just building upon the basic tools that we have. There's no reason you couldn't keep filtering, for other conditions as well. Okay, so let's execute this subset 2. Let's take a look at the dimensions, or maybe the number of rows, n row of this dat subset 2 has 24. So remember the original one had 2.5 million rows. The first subset down to that specific protein had 288. And now this specific subset down to this protein in a specific mass spec run has 24 rows. Okay, let's use the unique command on protein name just to confirm that in fact we have just this protein. That looks good. Let's use this on file name to make sure that we have just that file. Right, so this confirms that we've done the filtering properly. If we were to do file name on the first filtering, we would get lots of file names because we have best proteins for all the runs. All right. Okay, we already know about the view command, so you can take a look here. Let's look at view of this data frame. So we can see here for this particular structure of the data that we have peptides and some fragmentation ions for them. So we can kind of understand the structure of this better about what this data looks like. Okay, so this is a useful way to, as you subset, take a look at it so you can understand the structure that's there. Okay, so now we're going to go into this group by and summarize, and this is, one of the places where this is really powerful. So let's say we wanted to identify the number of unique peptide sequences identified for each protein in the data. Okay, if you were to do this in code, what columns? First of all, let's think about what columns you would need to do this kind of data analysis. Let's take a look at our input data here. We want to count the number of peptides for protein. Sort of the columns of interest are going to be the peptides and the protein. So a little bit of a no-brainer, but just sort of keying you into thinking about which columns are of relevance when you want to do an analysis. Okay, so then let's write a dplyr pipeline that does this particular task here. So this is a complex operation. We have let's actually find out. Let's note that we have some decoys here. We're going to deal with those later, but those decoys are going to be in this analysis. Let's find out how many proteins, unique proteins, are present in this data. So the first thing we can do is we can do dat $protein name to get all of the proteins names in our data. We can use the unique function to get those unique proteins. Let's assign that as a variable. So let's call this prots. And then let's count how many unique proteins we have. Okay, so we have 3,097 unique proteins present in this data set. Okay, and the question is, we want to determine the number of peptides for each of these 3,097 proteins. That would be a pretty big task to do. Do certainly by hand. You're not going to do it by hand. You wouldn't want to in Excel necessarily sort of select cells and then count things up by hand by dragging and dropping cells and so on. We can do this really conveniently using the dplyr syntax of group by and summarize, and this is all of the code here to do that. So we do this very complex sort of analysis with effectively 3 lines of code. So we take the input data frame, we group by the protein names, and then we summarize to create a new column called n peptides, and that is just the length of the unique peptide sequences. So I did this in 2 steps. Let me actually write this out explicitly. I did this in 2 steps above. I took prots equals dat protein name, and then from that, then I did the unique. Actually, sorry, let me do it like this way: unique prots. This will make it more clear. Unique on the prots like this. So I did something like this below, and our unique proteins are these, and there are length of those 3,097. So I did that in 2 steps. There's no reason we couldn't have done this where we do length function with the unique protein names. Okay, so this is a command where we've combined these effectively these 2 steps. Sorry, and then we have the length of unique prots. So effectively, we took these multiple, effectively there are 3 steps here and combined that into one line. That's what I've done here in a similar context for the peptide sequences. So got the unique peptides and then the length. This group by command will compute this, essentially this operation on each unique protein name. So let's take a look at what this output looks like. So now this is cool. We knew that we had 3,097 proteins, so we expect to get that many rows in the table. So now we have 1 row for each protein and the number of unique peptides that are present for those proteins. Okay. And we're not covering we're not covering this, but let me give you an example of what you might want to do. Let's assign this to a variable. Peps per prot, just give you a little preview of ggplot2 here. I encourage you after this course to go and investigate ggplot2, but we can make a distribution of the number of peptides per protein. Again, we're not covering this syntax in this course, so please just bear with me, but I want to give you a motivation for what you might do with this data. And please check out ggplot2 after this course, it's really useful. This is definitely more complex code. So if we write this code here, just give it a second, we now have a plot that shows the distribution of the number of peptides for protein from this data table. And we effectively got to this plot, by 3 lines of dplyr code and 1 line of ggplot code to get here. Okay, so fairly complex analysis that we did. And it's very straightforward. I mean, you can almost read this like English. Take our data frame, group by the proteins, and count up the number of unique peptides for each one of those. Okay. Any questions about that group by summarize? Okay, so this follows up on one of the questions that I talked to earlier about removing the decoy proteins, because we may not want those. So let's say we want to do this following task. We want to remove our decoys. We're only interested in the protein names and the sequences. Only keep the proteins that have at least 10 unique peptides per protein. And then I want you to, count the number of proteins for each peptide, and then order based upon the precursor mass. Okay, I mean, this example maybe is a little bit contrived, but maybe not so much. It makes maybe a little more sense. So let's write this dplyr pipeline. So I kind of helped us out here. I already have it here. Let's write this down step by step about what you would do. So first, remove the decoy proteins, then count by the number of unique peptides per protein, then filter those results to proteins that have at least 10 peptides, and then order results by the actually precursor mass. Well, I don't know. I guess I did something a little bit different here. We can try both of these things. So this is the pipeline that does that. So let's take this step by step. We already kind of saw this before, but let's take the first step here is our input data, and we're going to filter out our decoy proteins using the filter command. And as you recall, the first proteins, and we saw this above here as well, that these first proteins are decoys. So those have gone away now. Then we're going to group by proteins and count up the number of peptides per protein. So we've removed the decoys now. We should have fewer rows. We had, what did we have? 3,000 and what was it? 97. So there must have been, 3,097, including the decoys, we have 3,027. So, 70 of these were decoys, and we've got rid of those. So the number is smaller as expected. We have the number of peptides per protein. We see some of these have fewer than 10. So let's, fewer than 10. So let's filter those out. We got even fewer of those here. So now these are only proteins that have at least 10 peptides per protein. Let's assign this to a variable here and just make sure that that's the case. I'll call this dat2. And let's use the information we learned yesterday. Let's do the max of dat2 on the number of peptides per protein. I'm sorry. The maximum is 103. That's a lot. We want the min here just to make sure the minimum number of peptides is 10. right? So we filtered out things that were below that. So the minimum number should be at least 10, and that's the case. And then let's arrange this in descending order of number of peptides. I mean, this is useful. We might want to look at the peptides that we've covered the most in our experiment, right? So now we get this particular example where we have 103 distinct peptides per protein. So we really nailed the sequence coverage on this particular protein. Okay, you can imagine other, let's say, let's see, I think there are Q values in this table, but I guess they're not entered, they're NAs here. But let's say in theory that we had, we wanted to filter like to the FDR. All you need to do in the same pipeline is just write a new line in here, filter. Let's assume we have a column called FDR and it's less than 0.01. So, really easy thing to do. We just modified our analysis to include a false discovery rate filter, and we just add a new line with the filtering step. Okay, you can imagine doing other summaries here as well. Maybe you want to compute I don't know. Maybe you want to compute the average retention time. Probably doesn't make sense for proteins, would make more sense for precursor peptides, but I think you get the point that you can compute averages on retention time. You could compute averages on a precursor mass and then calculate ppm errors on those. You could just use those summarized commands to do those operations like that. So great. So sort of outline, sort of laying the foundation for doing some pretty sophisticated data analyses here using these dplyr verbs and combining them with pipelines to do some pretty complex analyses here. There's obviously a lot of depth here. There's a lot more behind the scenes that's going on, and you can take these pipelines to be much more complex. So I just encourage you to continue sort of working with these pipelines, try practicing them with your own work. And I think you'll really find that they're really powerful and will really streamline your day-to-day data analysis operations. So any questions here on the dplyr pipelines? So just reiterating, all of the exercises here are in our GitHub repository under the exercise section. I will upload those solutions that we just went through, so you can go and practice those line by line. I think you'll saw that I was taking bits of code and executing them sort of step by step. I'd encourage you to do that. I would encourage you to take these examples and modify them a little bit. Imagine we wanted, for some reason, to just get everything on the decoy proteins only, not the non-decoy proteins. How would you modify the pipeline to do something like that? So, okay, great. Yep, TAs, please interrupt if there's any questions you'd like to cover live. That covers the main content. I do have some wrap-up sections here that I'd like to go through to get you started on sort of where do you go from here, and some resources that you might take a look at and work with. Okay, just a summary of what we just talked about here. Okay, we've covered a lot of material. We've covered a lot of sort of the foundations. This is not by any means the entire breadth of the R ecosystem. It's not the entire breadth of the tidyverse ecosystem, but I would say these are really the fundamental pieces that will get you started to hopefully doing some interesting work with data in your day-to-day sort of data that you deal with. Even though these were basic things that we covered, I use these basics every day in the work that I do. So I think it is really helpful and really valuable. So what did we learn? We learned about RStudio and using the basics of R. In particular, we learned about making RStudio projects to help organize files. Please continue when you do your own work. Let's say you're going to make a new project. Please go into RStudio, make a project to organize your work, and then you can copy your data into that folder to make sure that you can access that data as you expect. And if you want to get back to an RStudio project, recall that you can, if RStudio is closed, let me close it. If you go back into find the directory where it's at, double click the rstudio.rproj file here. If you double click that, That will open up RStudio. It will open up your project. It will set the directory properly, and you can get back to work on that particular project that you're working on. And if you have multiple projects, you can go into File, close the project, and then go and open another project. And that's a nice way to organize your work. Okay, so we learned about R, we learned about RStudio, we learned about RStudio projects. We learned some basic syntax, just to reiterate the main points that we talked about. We learned about variable assignment. We learned about working with functions, and that we use functions on both vectors and data tables. We learned about subsetting data using the square bracket operator, and then conditional expressions. Remember, conditional expressions allow us to ask yes/no questions about our data. It's really useful for subsetting data to the pieces of data that we want to work with. We used those two main data types. We talked about vectors and we talked about data frames, also known as tibbles in the tidyverse ecosystem. We talked very importantly about reading data into R using functions like read_CSV. And then today we talked about the tidy data and using dplyr on these tidy data frames to do data manipulations and operations. So hopefully you can answer yes to all these questions. These were things that I had put up in the very first slide yesterday to talk about things that I hope we can accomplish by the end of this course, this workshop. So hopefully you can make RStudio projects and you can execute code. Hopefully you can create variables and vectors, and hopefully you can work with them. You can read data into R. You know about data tables. You can understand how many rows and columns are present. You can filter data. You can do summaries on that data using functions like min, max, mean, median, standard deviation, and so on. And then today we learned about tidy data. Now that you know about tidy data, when you communicate with other people, maybe in your lab or people that you work with, I know this happens to me a lot. People will send me data and they'll say, Ryan, I need some help. Can you help me analyze this data? But the data that they give me oftentimes is very messy. It's arranged in some weird formats. Maybe they've structured it in a strange way. Maybe there are some issues with the data. So I think if you understand the concepts of tidy data, you can communicate back to the people that you work with that say, hey, it would really help in the work that I need to do if you could structure your data in this way, or from your particular program, can you export your data in a certain way? That will really help me in my data analysis that I have to do. So it's really important to understand about tidy data and communicate those concepts to other people that you work with. That will streamline your ability to work with data. And then finally, hopefully you can now see some of the examples here to start doing some interesting data analysis with your own data using tidy inputs and dplyr pipelines. As I mentioned at the beginning, there's no way you can cover R in a 2-day workshop like this. So I hope that you will continue on your learning journey. Just let me give another endorsement for R. It's an incredibly powerful tool. Even if you have no intention of becoming a data scientist particularly, all scientists have to deal with data now in some way or another. And I would say even having just fundamental basics under your belt would be really useful. So I would say, hopefully you could continue your educational journey. There's a nice website here, education.rstudio.com, where they've collected a lot of really great resources here. A lot of stuff here I've covered today, but this is additional resources that you could go and look at. So, they have some information about installing R in RStudio. They have a gentle introduction to the tidy data in R, and so on. So lots of really great resources here. They have cheat sheets, books, and tutorials. So this is just a great resource for you to go and dig into more R-based resources, particularly for beginners. We've gone to this tidyverse website a couple times to look at those packages. It would be fun, I think, and worthwhile to go and just poke around that website a little bit to kind of see the breadth of the tidyverse ecosystem and maybe some additional packages that might be useful to you. We looked at the string R package as one example, but there are other packages there that might be really useful for your work. Let me point out 3 books here. And the cool thing here is that these are all very high quality books. These are written by experts who use and work with R and they're all free online, which is great. Let's take a look at this first one, hands-on programming with R. You can, if you want, you can buy the O'Reilly version of this as a hard copy, but the entire book is online for free. And just so you know, this whole website here was written using R, using essentially an R package called Bookdown. So the authors wrote this entire digital book, if you will, using R, which is really pretty cool. There's a table of contents here. You can go through the book, and the notion of this particular book is taking somebody who's new to programming and walking them through the very beginnings of working with R. So if you want to dig into sort of the R fundamentals in a lot more detail than I was able to cover, this is a great book to do it with. This next book here, I can't say enough good things about this. This is R for Data Science. This is written by Hadley Wickham here. Again, I mentioned him earlier with one of the quotes here. He is one of the biggest figures in the R community. Just a really great one sort of data scientist and software developer who has written packages like ggplot2. He's written packages like dplyr, and essentially is sort of the author, if you will, of this tidyverse ecosystem. He also works at RStudio. Very active educator, very interested in helping new users and new beginners get into R. Just a really great person in the R community. He has this book called R for Data Science. And this is an outstanding book that walks through the entire data science process of working with data. It includes data visualization with ggplot2. It includes some of the, or I'd say in more detail, the ideas we talked about with tidy data, with dplyr pipelines and so on, all kinds of stuff here. This book is also very accessible. I think it might be potentially a little challenging for a beginner to get through, but it is certainly something that a beginner could really benefit from. There is code. Let's take a look at this section on tidy data that I talked about. You'll see this quote here that I stole earlier on up here, but he walks through, he has the code that you can easily copy from the book. He shows the output of the data here. You can recognize some of these figures that I've used in my own teaching materials because it's so great, and just really walks through lots of these pieces of the things that we've worked on. So this is a great book. I would say if you're up to it, it's a great book to read cover to cover. It can benefit beginners to experts. It's a really great book, and it's free online, which is super. Let's go here. The last one I mentioned, ggplot2. Probably one thing that people want to do a lot here is to make plots. This is, again, Hadley's book, Hadley Wickham's book on ggplot2. Again, free online. You can buy the hard copy if you want, but this is all here free for you to use. This has a whole bunch of other additional syntax that we didn't go over, but talks about building plots with ggplot2. Again, this is, in my opinion, one of the, if not the most powerful and useful graphics plotting systems for any programming language out there. So I would certainly recommend, it's worth your time to learn it, and you can make incredible plots and graphs here using ggplot2.
Ryan, before we move on, could you, there's a question in Q&A. Could you show how to use write CSV function to save the tables as CSV files?
Thank you. Great question. Okay. So I think the question, yeah, obvious example. You have data and you want to give it to your boss, for example, or something. You need to save it out. Let me go back to our project where we can load some of this data. Let me do a multi-prong approach here because you're going to have questions after we're done. So let's do the following. Let's first go to our tidyverse website. Let's go to the packages, and then we can look through here to see what packages might sort of help us in this regard. So this readr package provides fast and friendly ways to read rectangular data. It can also write data here. So let's go into here because this looks like it might be useful. And there's a cheat sheet here. Let's take a look at that. I guess it wants to download it, which is fine. does the cheat sheet have right here? It does. So it talks about saving data, which I think is what we want to do. And so there is a function here called write.csv. And I do this not I went through this process to show you, like, if you have questions here, obviously you can feel free to email me. I showed you my email address. I'll go over that again. If you have questions like this, I'm more than happy to help with that kind of stuff. But if you're on your own, how would you get to this kind of solution? Well, this is one way you could do about, sort of look for R packages like I just did, and the tidyverse is a great place to start. And then you can think about maybe some packages that might make sense. And so we're going to use this write CSV function here to do that. Okay, let's go back to our code. We loaded up this, this particular case here. Let's read this annotations file here. Let's make a new script. Okay, so we're going to load the tidyverse package. We've done this a couple times. Okay, let's load that up. And let's read this data file with our read CSV function. I'm going to type CHO tab, read the annotations. This is our table. Let's just do a simple filter on this table. Let's call this DAT2. Not a great name, but let's take our data table and let's filter where condition equals condition 2, for example. But now we have a filtered data table. And let's say for some reason somebody wanted that table. You can now use the write CSV function to do that. If you want to learn about write CSV, remember we can use the question mark and write the name of the function without parentheses at the end and hit return, and it will bring up the documentation on that. And it says write a data frame to a delimited file, which is great. That's what we want to do. So this effectively will write this to a CSV file. These are the inputs to it. And there is some, I'll show you how to do this specifically, but if you wanted to understand what you need to actually provide to this function, you can look here and then scroll down here a little bit. You have to keep going. The first input or argument is a data frame that you want to write to disk. And the second one is the name of the file that you want to write it to. So let's do that. So we're going to write CSV. We want to write this data frame, and then we're going to give a name, migrate data.csv. I'm going to execute this code, but take a look over here in the browser. Okay, let's see what happens. It was hard, it went very quickly, but now we have this new CSV file that's been written to our RStudio project. Because we're using an RStudio project, it knows that it needs to write this data file to the project directory where we're organizing everything. So the project helped deal with our paths. If you didn't use an RStudio project, you would have written a CSV file. It would have gone to your default directory for your computer, which it will depend on your computer and things, but it would have gone somewhere else, and you probably would have never have been able to find it, or at least it wouldn't have been intuitive about where that data file went. So, but if you use an RStudio project and you open the project like I just showed you, you can just write the file out just like this, and it will go to your directory here. And then we could do, this kind of silly thing. Dat3 is read CSV, and we need to give the file name migrate CSV. Oops. We could read it back in. If we type dat3, we can see we get the same data table out. All right, so write.csv is the ticket for that. Great question. There might be some people or organizations to follow or just to keep up with that talk about R. Obviously, Professor Olga Vitek, obviously, her group writes really great packages. They publish great papers that deal with very specifically R packages like MS Stats, like Cardinal, that deal with mass spec data, proteomics data, probably that people here are interested in. So if you're if you haven't looked at her pack, I mean, obviously you're at this May Institute because you're learning about these things. So anyway, it's just a great resource to continue to follow her team and the work that they're doing. Bioconductor, let me briefly go here. Bioconductor is a repository for R packages around sort of the bio space. There is lots of stuff here that deals with genomics kinds of data, but there's also data packages here that work with mass spectrometry. So if we type mass spec, for example, here in the search field, you can see that there's lots of packages here. This is really small, hard to see, but lots of packages here. So we can see Cardinal here. This is one of the packages I just mentioned, and lots of other stuff as well, sort of related to mass spectrometry. And you might have, specific, might be in specific fields that deal with certain kinds of mass spec data. Worth it to come here and look through some of these packages to see if there's something here that might be useful. One package, somebody asked about reading mass spec files yesterday. One open format is an MZML file. There is a package here called MZR. Here, let me go to this particular package. This is a function that can read MZML files, for example. So MZR provides a unified API. This is a sort of an interface to common mass spec formats for mass spectrometry data. It comes with support for reading MZXML, MZML, and MZIDentML files, and so on. So if you come down here, you can take a look at probably this is a good reference here. It's an HTML sort of tutorial, if you will, about working with these files. And you can come through and they have some examples here about working with data. And this, for example, shows you about reading an MZML file and what you can do with it. And actually, this is kind of a nice tutorial to go through here, talk about plotting different things, looking at aspects of the mass spec data, and so on. I thought there were more examples here. There was another one that I was looking at that really goes into details. But in any case, Bioconductor is a great place for working for R packages, particularly for mass spec data analysis. RStudio, again, I noted this yesterday that RStudio is the piece of software that we were using to work with R, but RStudio itself is also a company. I mean, obviously not specifically related to mass spectrometry by any means, but RStudio as a company is really advancing the R ecosystem in lots of ways, providing support, funding, development for lots of these packages that we're working with today with dplyr and the tidyverse packages. So just as a company, if you're interested in R in general, that's a great company to follow in terms of what they're working with. Lots of information now happens on Twitter, either fortunately or unfortunately, and R is no exception to that. So you can look for hashtags like RStats here. I follow lots of people on Twitter just to see what interesting things are happening in R, in general, and people are doing really cool things all the time. Interesting analyses, interesting applications of R into, not only sort of scientific field, but in other cases, people are using R to make art. So there's a big movement making generative art using R. And people are doing some really cool things there. People analyze, financial data with R and all kinds of stuff. So if you look on Twitter for these hashtags, you can find lots of interesting things that might be of interest to you. On Twitter, there are some really prominent R users that keep you in the loop on what's going on. I've mentioned Hadley many times here. He doesn't post a ton, but usually when he posts, it's usually some, good quality, high quality stuff that he finds interesting. There are some other people here. These three people here are also prolific R tweeters. As with Twitter, everything isn't necessarily going to be based on R. You're going to get all kinds of stuff, but occasionally some interesting things on R will come down the line here. David Robinson, he's a big guy in the R community. He had a series. He doesn't do this so much anymore, but a couple of years ago, there was a movement known as Tidy Tuesday, where people would take a data set and they would live stream them working with a data set. They take a very raw data set and they would start doing things with it from beginning to end. And I think if you look them up probably on YouTube. He will have his old examples of that. Again, this isn't going to be specific to necessarily, obviously mass spec proteomics, but it is useful to see an expert like David take a data set and work through it. He'll use lots of the tidyverse concepts that we work through. And, he's a good statistician and does good data analysis. And so it's really great to see experts walk through data sets live. So he would be a great person to check out if you're interested.
Ryan, there's a question about bioconductor, like how are these submitted? How are the packages vetted, tested, or validated? What are the assurances on their performance? How is the support and all that?
Great question. So let's take bioconductor, but let's step out into the wider field of packages in general. And there's another repository for R packages known as CRAN, the Comprehensive R Archive Network. When you install the tidyverse packages, it goes to the CRAN to go and install that. It's the repository for packages. Then bioconductor is another separate place where you install packages. So that's a great question. And it varies. Package quality assurances about what they do is correct and right, and that things run, that they're performant, that they will run well on your computer. Those things are not necessarily guaranteed. And so there is a bit of caution about just randomly finding packages on the internet, on CRAN, that seem to do what you want. And when somebody might type in, like, I want to do this maybe sophisticated statistical method that I just learned about. And so they might type, in Google some of those ideas about this method, and great, they might find an R package that happens to implement this method. But take things with some caution. There's no guarantee that what that package does is the right thing. So ultimately, it's up to you on the end to really make sure that what these things are doing makes sense and that they're doing what you want. That being said, I don't know the specific, this would be a great question, and then maybe give a plug for some of the sessions next week at the May Institute. Kylie is going to give some sessions, I believe on Monday, that are going to be some more advanced sort of our work, kind of maybe build upon some of these fundamentals. And she's been an author of packages. Anybody on Olga's team has submitted their packages to bioconductor. So I would suggest asking questions to them about this, and they can tell you more about the process, because they've actually submitted packages through CRAN, and they can tell you about what that process is and how things get vetted. That being said, regardless, it's still, ultimately falls on you as the end user to sort of be responsible for things that come out. Nothing is bug-free. Software that's complex like this, may have bugs. Obviously, people write high-quality packages, not saying that there are necessarily bugs in there, but ultimately, you have to use some caution. I think you have to also trust the groups that are building these packages. So anything in the core tidyverse packages are developed by experts that have good practices in place for testing their code. Like anything written by Hadley Wickham is going to be really high quality, that they go to great efforts to make sure the quality of their code, the correctness of their code, and these things are of high quality. And so things coming out of the core tidyverse packages are going to be high quality, and you can expect that those things are going to be things that you can hopefully trust. Again, not saying that there aren't bugs, there are bug fixes that come out all the time, but usually they put a very high level of rigor into the packages that they write. So that's kind of the question, the answer, that there is no clear guarantee that any package that you have is going to be bug-free. They're going to do exactly what it is, but put some research into the people that write the packages, and if you trust them for what they do, then that's a good sign that hopefully their packages are also trustworthy. And the converse of that is be wary of just grabbing any random R package off the web that you happen to find as a possible solution to what you would like to do. Let me give you another example with the CRAN. There is a process that you have to go through to get your package approved. So it's not that anybody can just submit a package and it shows up. There is a process that checks the package, but those are more technical checks about does the package compile correctly? Does it run some basic tests correctly? So it's more about operational aspects of the package rather than correctness of the package. So kind of to segue from that question, where do you go to get help? So Google is a good place to start. And if you get an error message, like let's just make one here. Let me misspell this data file, okay? And let's try to run this function. Not right. Shoot. I changed the name of the file in the right function, and you'll notice here that I just wrote a new file here with the I'm misspelling here. That's not what I intended. I wanted to read a file with a typo in it. Let me execute this command. So we got an error here. So obviously, so the error message is something useful that you can use in Google to search for. The things specific to you, like your typo, there is no reason to expect that your specific typo should show up on the web, right? So this part of the error message is not useful. This file path on my computer also isn't probably useful because that generally shouldn't expect to show up on the web, but maybe this particular piece of the function would be useful, this error message. So let's go to Google. Let's type the name of the function, which was read CSV, and then let's put in quotes the error message here. And obviously this is Google. You're going to get all kinds of messages here. This is one of the resources I'm going to recommend, this community.rstudio.com. If you get a result from here, that would be a great one to follow up on. So let's do this. Let's see what it has to say. Working on something. This file does not exist in the working directory. Anyways, they go through here and they talk about sort of ways in which you might address that question. Okay, so that's sort of a general thing you can do. Use the error message text and put those in quotes in Google to help with that. R is an unfortunately named language because, as you can imagine, if you want to search the web for the letter R, you're going to get lots of hits. Google has gotten better about this, but if you're going, you can't just put necessarily R in front of your search term and expect to get relevant results. So try to add some specific terms that will help out, like the names of your function, like things like tidyverse, and so on, and that can help guide your search. So that's a case where the name of the language compared to Python, which, you know, where the Python is more a little more helpful for Google searching, R is not. So you sometimes have to add some additional terms there to hone in on what you're looking for. Stack Overflow, you probably know about that if you've done any kind of coding. Can be useful, but it's really a mixed bag. I see lots of advice on Stack Overflow that I don't agree with, particularly with R, and particularly if the posts are very old. So look for dates on the posts. They can be useful sometimes, but just treat it with treat things with a grain of salt. I know it is a common practice sometimes to copy and paste code verbatim from Stack Overflow. You know, that can be useful, but I just say kind of with that question about the packages, just be mindful of that and just be a little bit careful that copying and pasting off of Stack Overflow without any additional thought or oversight can get you into problems. This RStudio community, we just looked at an answer from that, but this community is really friendly, particularly to beginners. And so you can search their chat base here for questions here. There's lots of good stuff. You know, you may just want to dig through this a little bit to see if there's questions here that might be relevant to you. And then you can also use this as a place to ask questions. And generally speaking, people are very friendly to new users asking questions about R. I think the main thing that you want to do is you want to search first about your question, because if somebody's already answered your question, it's just kind of common courtesy to try not to ask questions that have already been answered. And so I would first search as best you can to see if your question has been asked and answered before. If it hasn't, then you can submit questions to here. And like I said, this is a really welcoming community for particularly for beginners. So that's a great place. Last plug. If you're really interested in R and you want to get into it, I highly suggest looking for, if you have access to one, a local R users group. The R Consortium and RStudio, they support R users group throughout the world. And they're usually really great, nice, friendly communities where you can go and interact with other R users. I'm in Southern California, so I run the Southern California R users group. And, I've been doing that for, goodness, 5+ years now. We've grown to a really big group of people. COVID obviously has made things really weird, but before COVID, we used to meet on a monthly basis, and we get together, we network, we talk with other people, we learn about various things about R. We'd usually have a speaker come in and give presentations to learn about R, learn about how people are using data science methods in R and other fields, and just usually the community is really nice and welcoming. So I highly recommend, if you're interested in really digging into R, find an R local R users group and go and check them out. I know sometimes it's maybe not as comfortable to just go out and go into a community that you've never been to before, but usually these groups are really really welcoming of beginners, and I found it to be a really great place to meet and interact with people. All right, so we're wrapping up here. Obviously want to thank Olga for organizing this May Institute, allowing me to be a part of it, to our TAs that managed all these questions that come through. It is definitely more challenging, both I think from on your end as a participant, but also on the presenter side, to give these kinds of workshops, particularly for beginning kind of things where it really would be helpful to be in person, where we can come and interact with you directly. But thank you for the TAs here to really make this something that we can actually do online and hopefully be able to execute this in a way that is useful to everybody. So thank you very much for the TAs for doing the questions here, and then also all the participants. I mean, you're here on a 2-day fairly intensive course here, particularly on Saturday here today. So thank you very much for coming through and joining us today. Hopefully, with the resources here and the material we covered, I hope that this has been useful for you. And what I would recommend is maybe try to take an analysis you did, like in Excel, and try to go and maybe start simple. Start with a simple analysis you did in Excel, and go and see if you can write an R script using the tools that you learned today, to see if you can reproduce that analysis in the R script. And then you can check your results back to the Excel results and see if they agree. And I think that would be a great next step to get you using R on a daily basis on your sort of the data that you work with. One last thing, just note that if you go to the May Institute website and you go to the documents, here, feel free to reach out to me. My email address is here. I'd be happy to answer any questions, any input, advice you might want about R. Like I said, feel free, send it along, and I will get back to you as soon as I can. I also wanted to just give a plug for the May Institute. This was the first week, but it continues next week. And lots of really continued great sessions here. As I mentioned, Kylie here on Monday is going to cover an intermediate R crash course. So she's going to be building on lots of the things that we talked about in the beginner tutorial. If the stuff that we went over these last 2 days sort of made sense to you and you felt like you had a good handle, I'd highly recommend going to Kylie's session. She's a great educator here, and she will sort of take the next steps here. If this stuff was all really easy for you, I highly recommend going to her session here. So that would be great. Lots of other great sessions here. Learning about MS Stats is a great piece, and MS Stats TMT, if you're doing TMT based work, these really great packages about using them from their authors and the experts on these. So highly recommended. Just lots of other great stuff. And then if you're on the Python side here, this was also it looks like a really great session here where Charles is going to talk about best practices for Python development, really important for reproducible data analysis. If you know some Python and or want to learn about some of these things, this might be a more advanced kind of session, but could be really useful as well. So just plugging the second week of the May Institute. If you haven't registered for the second week, you should be able to do that online. To get the info to join these kinds of these great sessions for next week. Great. So we're right about 11:14 here, so 1 minute left, but I'll be happy to stick around if anybody has any questions. And feel free to bring them up, and feel free to email me if you have any questions after the course as well. So I suspect everybody's probably ready to go and enjoy their weekend. Sai and Bartika, thank you very much for TAing and answering the questions. I think, obviously really helpful there.
Thank you.
Yeah.
Thank you, Ryan.
I'm sure we'll have sort of a recap here kind of at the end as we go through things, but thanks again, and thanks to anybody still sticking around. Have a great weekend, and yeah, we'll follow up soon. So take care, everybody. Thank you.
You too.